Discovery clears the tower.
Discovery, go and throttle up.
Discovery, roger, go for deploy.
H2 and everybody in the shuttle program, the crew is go for launch.
Roger, nice to be in orbit.
We have followed in their footsteps to get us where we are today.
You are looking live at a view of the SpaceX Dragon Endurance, currently mated to the forward port of the Harmony module of the International Space Station as the vehicle flies 262 miles from northwest to southeast over the Atlantic Ocean off the east coast of the United States. Good afternoon from Mission Control in Houston and the International Space Station Flight Control Room as 4 crew members who have spent almost 5 months aboard the orbital outpost begin the journey home, heading for a splashdown off the coast of California on Saturday morning to wrap up a 148-day, 62.7 million-mile mission. Welcome to our coverage of the departure and hatch closure of the crew-10 crew from the International Space Station.
Go ahead on 2, Tuck.
Hey, Tess, we have been trying to call SpaceX on both Big Loop as well as drone DG1, but no response. Also, did you guys hear us?
And Tuck, yes, we heard you. We do not currently have TDRS Direct on Dragon, so our return calls did not make it up to you.
Okay, so can you guys relay the information to SpaceX? So step 2.9 is complete. Dragon cabin config for departure is complete. And also we are looking for go for step 3.1 and also checking the LIO config in step 3.4.
Checking.
Japan Aerospace Exploration Agency astronaut Takuya Onishi, who spent some time as the commander of the International Space Station up until a few days ago.
We have you loud and clear now, too. Thank you. And SpaceX Dragon, come check.
The conversation you've been hearing, part of the pre-hatch closure preparations.
Currently is not on Space to Ground 2 directly. We're working the config on the ground to get you comm.
You heard the voice of spacecraft communicator Tess Caswell here in Mission Control.
We have seats 2 and 3 seated and in seats 1 and 4 working on steps 2 and 3, or correction 3 of 2.103.
And that was the voice of Dragon Commander, Crew-10 Commander Anne McClain of NASA, as she and her 3 crewmates begin to put themselves in their seats in the SpaceX Dragon vehicle, named Endurance, and begin the process of suiting up for hatch closure and the undocking of Dragon from the forward port of Harmony that is scheduled later this afternoon at 5:05 p.m. Central Time, 6:05 p.m. Eastern Time. You're looking at part of the complement of the Expedition 73 crew that will be left behind once Endurance departs, with the undocking scheduled about 2 hours and 15 minutes from now. Again, the 4 departing crew members, Anne McClain and Nicole Ayers of NASA, Takuya Onishi of the Japan Aerospace Exploration Agency, and Roscosmos cosmonaut Kirill Peskov. They launched aboard their Dragon vehicle on a Falcon 9 rocket on March 14th, arrived at the International Space Station the following day, and at the time of splashdown that is scheduled for 10:33 a.m. Central Time, 11:33 a.m. Eastern Time on Saturday morning, Crew-10 will have completed 148 days in space, 146 of them aboard the station, a journey of 2,368 orbits of the Earth and 62.7 million miles. Anne McClain's 148 days in space upon splashdown tomorrow will have totaled 352 days in space on her 2 flights. Nicole Ayers, of course, in her first flight, 148 days. Takuya Onishi, with his 148 days in space upon his return to Earth tomorrow, will have logged 263 days in space on a pair of flights. And this, the first flight for Kirill Peskov, he will have logged 148 days in space. The crew saw a total of 5 arriving vehicles and the departure of 6 visiting vehicles.
SpaceX Dragon has you loud and clear. Great to talk to you today.
Hey, Ann, great to hear your voice. Sorry for the delay there. Capcom is about to relay up a call, but captured all of your words, and you are go for 3.1 for LIO config, IMV teardown, hatch closure, and suit donning. We're going to be swapping to cartridge number 4 today.
Copy, go in step 3, cartridge number 4.
And that conversation between the core, the crew operations resource engineer, basically the SpaceX Capcom or communicator, and Anne McClain aboard Dragon, as she indicates that the crew members are inside Dragon. They will swap out lithium oxide canisters that are used for the scrubbing of the air to remove carbon dioxide from the atmosphere on board the Dragon during its free flight away from the International Space Station. This will be basically a 17.5-hour transit of phasing away from the station following undocking later today until the time of the deorbit burn for Dragon that is scheduled for Saturday morning at 9:39 and 47 seconds a.m. Central Time, 10:39 and 47 seconds a.m. Eastern Time. The remaining crew that will be left on board the station to continue the unbroken presence of humans aboard the International Outpost, which will reach its 25th anniversary on November 2nd this year, is comprised of the new station commander, Sergei Ryzhikov, his Roscosmos colleagues, Alexei Zabritsky and Oleg Platonov, NASA astronauts Johnny Kim, Zena Cardman, and Mike Fink, and Kimiya Yui of the Japan Aerospace Exploration Agency. Ryzhikov, Zabritsky, and Kim launched back in September on the Soyuz MS-27 spacecraft from the Baikonur Cosmodrome in Kazakhstan. Cardman, Fink, Platonov, and Yui launched just 8 days ago aboard the SpaceX Dragon Endeavour, arriving at the International Space Station to begin their tour of duty on board the orbital outpost. A good view once again from external cameras on the International Space Station of the docking interface between the forward port of Endurance on the left and the pressurized mating adapter on the forward end of the Harmony module and the U.S. segment of the International Space Station. The cone-shaped object at the top of your screen is the nose cap on the Dragon itself, which will be closed prior to Dragon's re-entry back into the Earth's atmosphere on Saturday. After waving off the undocking of Dragon because of weather conditions off the coast of California, a final weather briefing was conducted this morning by NASA and SpaceX managers. The weather conditions were carefully evaluated and determined that winds at the splashdown site off the coast of California are and will be within limits tomorrow morning.
SpaceX Dragon on big loop for LIO.
Go ahead, Dragon. We're with you on the big loop.
Hey, LIO cartridge number 4 has been installed in active slot at GMT 1955.
We copy. LIO cartridge 4 installed in active slot at 1955.
And once again, Takuya Onishi confirming with SpaceX flight controllers in Hawthorne that the air scrubbing canisters have been installed aboard Dragon to help with the scrubbing out of carbon dioxide during Endurance's free flight away from the station through the time of entry and splashdown on Saturday morning. The countdown clocks here in Mission Control are counting towards the command that will be issued 2 hours, 3 minutes, and 30 seconds from now for the retraction of an umbilical that is basically a power and telemetry cable that has provided power to Endurance during its 5 months attached to the forward port of the International Space Station. Once that umbilical retracts, the command that will previously be issued begins the opening of 2 sets of hooks, 6 hooks for each set, that have held Endurance firmly in place to the forward port on pressurized mating adapter number 2 on the forward end of the Harmony module. Once those hooks are opened later today, there will be the first of 2 undocking burns, as they are called. The first for 1.5 seconds to begin the physical separation of Endurance from the International Space Station. The second burn of 5 seconds in duration will accelerate that opening rate and lead to the beginning of 4 so-called departure burns, which will increase the phasing away from the station for Endurance to a safe distance for the deorbit burn that is scheduled for Saturday morning. Earlier this week, the departing Crew-10 crew members, led by Commander Ann McClain, had a few moments to share their thoughts with the Expedition 73 crew members that they were part of and continue to be part of until they undock later this afternoon. That all led into a change of command ceremony in which Takuya Onishi of the Japan Aerospace Exploration Agency handed over station command to Sergei Ryzhikov of Roscosmos. McClain's comments were particularly poignant. Let's take a moment as we replay her comments this past Tuesday as the Crew-10 began preparations to begin their trip home.
And as we complete our mission on Space Station, we really want to lead with gratitude for the absolute privilege of getting to live and work aboard this amazing International Space Station. All of us are keenly aware that we may never get to do this again, and we've been very pensive over the last days of understanding what we have all got to be a part of. And we know that there's some tumultuous times on Earth, and there's some people that are going through struggles all around, and we want this mission, our mission, to be a reminder of what people can do when we work together, when we explore together. The foundations of this mission were laid long before any of us got here. This is a short snapshot in time today in our mission. But the International Space Station, this international mission that has been going on for almost 25 years, was made possible by visionaries who years before believed in something this massive. I truly believe that this is one of the biggest feats of cooperation that humans have ever accomplished. It takes people from every country all around the world every single day showing up to support this mission to make it happen. And really, we just get to be, we had the privilege of getting to be here for a short period of that time. But if we think back to 40 years ago when this idea was conceived and the international partnerships started to come together, The atmosphere and the climate politically was very similar to what it is now. There's a lot of people that would say that's not going to be possible. But all it took was visionaries from all around the world to work together, to have a mustard seed of faith that something like this could be done when we work together. Crew-10 has had the absolute privilege of working here for the last 4 months, and we have so much gratitude for all of the ground teams that showed up every day to make this possible. We truly are very humbled to represent humanity, and we hope that we can be a reminder to others of the goodness of humanity and what we really can accomplish when we work together.
Once again, those words from Dragon Commander Anne McClain of NASA this past Tuesday during farewell remarks at the beginning of a change of command ceremony. So as we fast forward now, the 4 crew members who are departing the station, McClain, Nicole Ayers, Takoya Onishi, and Kirill Peskov, are aboard Dragon, preparing to configure the systems on their spacecraft before they close the hatch and begin suiting up into their launch and entry suits. Once the hatch is closed, there will be leak checks on both sides of the docking interface that you see there from external camera views on the station. Those leak checks will ensure that we have an airtight seal before we begin to depressurize the small passageway or vestibule that connects Dragon to the forward port of the Harmony module through that pressurized mating adapter on the right side of your screen. Once the vestibule is depressurized and the pressure is equalized on both sides of the docking interface, that will set the stage for the undocking command to be issued by SpaceX flight controllers in Hawthorne, California. That's scheduled 1 hour 57 minutes from now, 5 minutes after that command is issued, and with all 12 hooks holding Endurance to the International Space Station opened. The first undocking burn of about 1.5 seconds in duration will be issued, and that basically breaks the interface between Endurance and the station and marks the official undocking of the vehicle from the orbital outpost. The International Space Station is currently traveling in an orbit 262 miles above the Earth, moving from northwest to southeast across the Atlantic Ocean east of the continent of South America, about to enter an orbital sunset. The station, of course, orbits every 90 minutes in an inclination of 51.6 degrees to either side of the equator. We now have received confirmation that the hatch on Endurance is closed, so we'll mark that at 3:04 p.m. Central Time, 4:04 p.m. Eastern Time. Again, the hatch closed to the Dragon Endurance.
SpaceX Dragon, PPRV ISO valve confirmed visually open.
SpaceX copies on the big loop.
And this view inside the Dragon Endurance with the hatch to the International Space Station's Harmony module having been closed through pressurized mating adapter. Number 2, you're looking at crew members who are configuring systems prior to completion of their suit-up procedures that will lead to their undocking at 5:05 p.m. Central Time, 6:05 p.m. Eastern Time. Again, this is a 17.5-hour transit away from the station to a splashdown site off the coast of California on Saturday morning. The deorbit burn on Saturday morning at 9:39 a.m. Central Time, 10:39 a.m. Eastern Time will be a 17.5-minute retrograde firing to slow Endurance down by 115 meters per second, allowing it to drop out of orbit for its high-speed entry back into the Earth's atmosphere. About 18 minutes after the deorbit burn, there will be the claw separation that basically holds the trunk in place, followed by the trunk of Dragon, the lower portion of Dragon. That will separate at 9:58 a.m. Central Time, 10:58 a.m. Eastern Time, before Endurance is maneuvered into the proper orientation for entry with the heat shield facing in the direction of travel to ablate or repel heat that will build up around the spacecraft to about 2,500 degrees Fahrenheit. There will be a brief period of loss of signal because of the ionization of molecules around the spacecraft itself. Once we come AOS, or the acquisition of signal following that period of ionization, we'll be set for the deployment of the drogue chutes on Endurance, followed a short time later by the main chute deployment. Splashdown is scheduled at 10:33 and 47 seconds a.m. Central Time, 11:33 and 47 seconds a.m. Eastern Time. That will be 8:33 a.m. off the coast of California. Again, splashdown scheduled on Saturday morning.
Dragon, SpaceX on the big loop. Control of cabin air temperature via 4.080 is allowed until pre-chill. Note that the hex is currently configured for maximum cooling.
Is 4.080.
And the view inside Dragon, you're looking at the crew members who are completing their suit-up procedures. On the very right side of your screen is Takoyo Nishi and Kirill Peskov, already in their seats, Nicole Ayers and the Dragon commander, and McLean. The undocking and departure profile off the forward port of the International Space Station's Harmony module will carry Dragon to a distance of about 400 meters in front of the station, and then a similar distance above the station and behind the station as the departure burns carry Dragon into a trajectory that will result in it phasing away from the International Space Station over the course of about 17 hours prior to the deorbit burn that will ultimately bring Endurance home. Once again, the mission will wrap up tomorrow morning, with Crew-10 having spent 148 days in space, 146 of them aboard the station, a journey of 2,368 orbits spanning 62.7 million miles. during their mission, the 4 crew members of Crew-10 conducted a multitude of scientific experiments, and Dan McLean and Nicole Ayers conducted 1 spacewalk totaling 5 hours and 44 minutes in duration. This will be the 4th time that a Dragon will have splashed down off the coast of California. The FRAM-2 mission, the commercial resupply uncrewed CRS-32 mission, and most recently the Axiom-4 mission, all concluded with splashdowns off the coast of California, but this will be the first time that a Dragon involved in the commercial crew program will have returned to Earth with a splashdown off the coast of California. And in the near field of view, Roscosmos cosmonaut Kirill Peskov completing his suit up and his strap in to his seat. If you're just joining us, the hatch to the Dragon Endurance, that is the vehicle bringing home the Crew-10 quartet, was closed at 3:04 p.m. Central Time, 4:04 p.m. Eastern Time. You're seeing the crew members completing their suit-up procedures. There will be leak checks on both sides of the docking interface between Endurance and the forward port of the Harmony module of the International Space Station through pressurized mating adapter number 2. Once those leak checks are complete, the small passageway at the docking interface will be depressurized to vacuum. That will set the stage for the undocking command to be issued 1 hour and 46 minutes from now. That will come right on the dot at 5 p.m. Central Time, 6 p.m. Eastern Time, initiating a 5-minute procedure to retract the umbilical between Dragon and the International Space Station, that umbilical having provided power and telemetry to Dragon during the course of its almost 5 months of docked operations. 2 sets of hooks, 6 hooks per set, will then be opened. Set 1 first, followed about 2 minutes later by set 2. And then the first of the undocking burns, a quick burst of the Draco thrusters on Dragon for about a second and a half, will be initiated at 5:05 p.m. Central Time, 6:05 p.m. Eastern Time, to initiate the actual physical separation of Dragon from the International Space Station. While we have a handover in our downlink video from the station through our tracking and data relay satellite system, you're looking at Flight Director Allison Bollinger on the right side of your screen, joined to her right by spacecraft communicator Tess Caswell, who has been talking to both the departing Dragon crew and the Expedition 73 crew, who remain on board the complex. For Sergei Ryzhikov, Johnny Kim, and Alexei Zabritsky, who launched aboard Soyuz back in September, the Soyuz MS-27 spacecraft. This is their 123rd day in space. while the Crew-11 crew recently arrived at the station, consisting of Zena Cardman, Mike Fink, Kimia Yui, and Oleg Platonov, are in their 8th day in space. And on the left side of your screen, you're looking at the back of Mike Fink, veteran NASA astronaut, now in his 4th flight into space, as he and his crewmates are doing seal inspections on the forward hatch to the Harmony module that will be closed a short time from now, initiating the beginning of the equalization of pressure and the ultimate depressurization of that vestibule, very short passageway between Dragon and the International Space Station.
Dragon Houston on 2.
Houston Dragon, go ahead.
Stand by for Big Loop RF audio config. And we expect this to cause approximately a 2-minute dropout in audio with MCC.
See a 2-minute dropout, and for everyone's awareness, we are starting section 5 of 4.010. All 4 crew members are seated, and strapped in.
That conversation referencing the Big Loop, that is the interconnected communications channel that ties the space-to-ground loop aboard the International Space Station with the communication system aboard Dragon, and which will remain in play until Dragon departs the so-called approach ellipsoid, which is basically a racetrack boundary outside of which the integrated operations between Mission Control here in Houston and the SpaceX Mission Control Center in Hawthorne, California is conducted. Once Dragon departs the approach ellipsoid, the work is essentially done for Mission Control here in Houston for the joint phase of this mission, and SpaceX Mission Control will take over full operations of Dragon's departure, its back away and phasing away from the International Space Station all the way through splashdown on Saturday morning off the coast of California. The space station is currently flying 262 miles south of the continent of Africa, about to begin a southwest to northeasterly trek that will carry it across the east coast of Australia and back across the North Pacific And as you can see on the left side of your screen, the hatch is now closed on the station side of the docking interface. As Zena Cardman cleans up some of the equipment prior to the start of the leak checks that will be conducted between Dragon and the International Space Station to ensure that we have a tight seal before the depressurization of the passageway that will be the precursor to the undocking of Endurance from the station, physical separation scheduled at 5:05 p.m. Central, 6:05 p.m. Eastern Time. The communications loops have now been properly configured according to flight controllers here in Houston.
SpaceX, Dragon on the big loop. Houston Dragon, we have you loud and clear.
All right. C2V2 RF config is complete on the big loop, so you were just about to call SpaceX. We'll let that be your comm check.
And Dragon, SpaceX has you loud.
Thanks, Tess. Thanks, Cronus. SpaceX Dragon, we are complete with.
Okay, SpaceX has you loud and clear on the big loop.
Complete with suit donning. We are at 4.011. Looking for your go on 1.1.
Dragon, you are go to begin suit leak check procedure 4.011.
And McLean talking to both the Capcom here in Houston and the core, or SpaceX Capcom in Hawthorne, California, if you will. The procedures that they're relaying back and forth now have reached the point of leak checks on their suits to ensure that they have a tight seal on all 4 suits for the departing crew members.
Standing by for your go. Close the 8-pass hatch.
And Johnny, before we give you that go, we'd like to confirm that you saw no damage or debris in your inspection in 5.2.
Confirm, no damage or debris, clean seals on in step 5.2.
You are go for step 5.3.
Work.
NASA's Johnny Kim talking to Tess Caswell, the Capcom here in Houston, as they are about to complete the series of hatch closure procedures, this being the final hatch between the pressurized mating adapter and Harmony itself, that will set the stage for not only the suit leak checks for the 4 Dragon Endurance crew members, but also set the stage for the depressurization of the vestibule connecting Dragon to the International Space Station. We want that vestibule to be depressurized down to vacuum with readings that are equivalent on both sides of the docking interface before we move into the undocking command later this afternoon that will set in motion the physical separation of Endurance from the complex and begin the journey home for the 4 crew members comprising crew-10 Ann McLean, Nicole Ayers, Takoya Onishi, and Kirill Peskov.
That's Dragon on the big loop, step 2.2, ready to pressurize.
Dragon, you are go to initiate suit leak check.
Copy, go.
And McLean, the Endurance commander, indicating that the crew is about to pressurize their suits to ensure that we have tight seals and good integrity on the 4 suits for the departing crew members.
Houston copies.
Leak checks underway for the 4 suits. About 1 minute left before we should hear from SpaceX that we have 4 good suits.
Dragon, SpaceX, on the big loop, we see 4 good suit leak checks.
Green copies, good suit leak check.
And as you heard in that communications, 4 good leak checks performed on the suits, being worn by Ann McLean, Nicole Ayers, Takoya Onishi, and Kirill Peskov, with their crew members who soon will be departing the International Space Station, all buttoned up now, conducting final pre-departure preparations. We will point towards our next broadcast that is coming up at 4:45 p.m. Central Time, 5:45 p.m. Eastern Time, when we here in Houston will be joined by our colleagues in Hawthorne, California at SpaceX Mission Control for the undocking of Endurance from the International Space Station and the beginning of the trip home for the crew-10 crew members. So again, the hatch is closed, the suits have been verified to be airtight, and the stage is set for the departure of crew-10 from the International Space Station about 1 hour and 34 minutes from now. With that, we'll sign off this broadcast, and we'll be back with you in about 1 hour and 15 minutes for the undocking of Endurance from the International Space Station. In the meantime, this is Mission Control Houston.
density is not going to make it into the atmosphere and intact onto the Earth, okay? So you would have an airburst, for example. Whereas if you have a really dense object like this iron meteorite, it'll punch right through the atmosphere, even if it's a small object. And then it will create a crater like the meteor crater we see in Arizona. So what do these meteorites tell us, right? Why do we need to characterize these objects? So by understanding the composition, we can figure out what is the mitigation mechanism we're going to use, because the tools we would use vary vastly depending upon what they're made of. To understand what asteroids are, you have to go back to kind of the beginning of our solar system.
Asteroids are rocky bodies that are kind of leftover fragments from when our solar system first formed a long time ago, more than 4 billion years ago.
The major planets formed when the first solids condensed out of the solar nebula. These solids slowly coalesced, came together eventually to form what you call as planetesimals. These are objects that are, a few tens to a few hundred kilometers across. And you had, internal heat, that led to what you call as differentiation. They'll have a core, a mantle, and a crust. So these iron meteorites we see here represents the cores of those planetesimals. So we believe that there were more than 100 planetesimals that differentiated between the orbits of Mars and Jupiter. But most of these planetesimals were destroyed catastrophically due to impacts over the next few 100 million years. And what we see now in the asteroid belt are remnants of those catastrophic destructions.
Most of the material that made up our solar system kind of got swept up into the sun and to the individual planets, but not all of it.
It's kind of like shattering a plate on the floor. You have a few big pieces, but lots and lots of small pieces.
So asteroids are kind of those leftovers of the formation of the solar system. A lot of them keep their distance very nicely in the asteroid belt between the orbits of Mars and Jupiter. But some of them over time, because of being tweaked by the gravitational pull of Jupiter and whatnot, have made their way into the inner solar system. And so some of these leftovers from the formation of the solar system can get a little too close for comfort to Earth.
That's how we end up with near-Earth asteroids.
We'd really like to understand the distribution of these objects, their compositions, and kind of where they come from.
So that's what we're trying to find out.
How do they leak into the inner part of the solar system and get into this region near the Earth's orbit?
You don't want to just know that the asteroid is there. You want to know, how large is it? What is it made of? So there are telescopes that then go out and study particular characteristics of asteroids to the extent they can from the ground.
So we want to find out what is the composition of the object, how fast it's spinning, whether it's one object or two objects, and of course we want to know, the mass of the object. And for that we need to have an accurate idea on its size. That's where radar comes into play.
Yeah, that's cool to finally see it.
This is the biggest one in this complex. It's 70 meters in diameter. All the other ones are 34. This is the most powerful planetary radar on Earth. So here we are at the Goldstone Solar System radar in the middle of the Mojave Desert, about a few hours drive from Pasadena, the Jet Propulsion Lab. This is where I connect remotely to observe near-Earth asteroids. I'm Shantanu Naidu. I'm an asteroid radar researcher here at NASA's Jet Propulsion Laboratory.
Oh, that's amazing.
Whenever an asteroid comes close to Earth, we use this radar to observe it, which can tell us about the shape of the asteroid. It can show details on the surface of the asteroid, such as ridges, concavities, craters. We can also measure the precise distance to the asteroid.
And then from all of that, you get really fantastic science, and then you get that information you might need in the event an impact threat is discovered.
So radar is an active form of observing an asteroid in the sense that we generate our own electromagnetic waves. We use really high power transmitters to transmit electromagnetic waves in the direction of the asteroid. The asteroid reflects these waves They get distorted during this process and they come back towards Earth. So you have signals from space coming in, reflecting off the primary dish, reflecting onto the secondary dish, and then they reflect onto the instruments. We can compare the distorted received waveform with what we sent, and using this comparison, we're able to generate highly detailed images or maps of the asteroid. So one example I can show you is 2024 MK, which was a recent target that we observed. We were able to obtain these very high resolution images where each pixel is under 2 meters in resolution. If I zoom in here, you can see all these intricate details on the surface of the asteroid. Like you can see these radar dark regions, you can see it's a very irregular shape. There's a lot of things that look like ridges, so we can track these features and we can measure the spin rate of this asteroid. So there's a control room in the pedestal. This is where the telescope operators sit. We send them the orbits of the asteroid, we send them the observing plan, we send them the configurations we want to observe the asteroids with. So this is where the telescope operators sit, and this is where they control all the equipment from, and that's where the data gets collected in the computer behind, and that's what we connect to download the processed images at JPL. This seems like a nice setup, so I'll send it to the telescope operators. When we start observing an asteroid, we need a very accurate orbit so we can point accurately at the target. We get a spectra, update the orbit, we get a coarse resolution image, we update the orbit again. And so we transmit for a fixed amount of time, which is the round-trip light time to the asteroid. And as soon as that time elapses, that is when we start receiving the echo, we switch from the transmitter to the receiver. It takes a few seconds to travel a few million miles back into space and reflect off the asteroid. So we transmit for an entire round-trip time, and then as soon as the echoes start reaching back to the telescope, that's when we switch to the receiver. And then we record the whole transmitted wave, so for one round-trip time, and that constitutes one image. And once we get a good orbit, we can start getting these higher resolution images. It's always exciting because it's the first time anyone is looking at the features on the surface of this asteroid. Most of the asteroids that we observe, we've not seen them before, and so whatever you see with radar is a surprise, and a lot of the times it's discovering something new. It is very cool to know that at least for a few minutes, or maybe even a few days, you're the only person in the world who knows this thing. It's very exciting. It's a very exciting feeling. There's a sense of responsibility, knowing that I'm part of such an important team, and we're all tackling such an important problem of asteroid threat assessment and mitigation.
Let's say we discovered something and we only had a small window to observe it and quickly turn around information about its properties.
What if we find an asteroid that's going to impact the Earth next week?
Then all of a sudden an opportunity came up that nature gave us. An asteroid designated 2023 DZ2 was discovered.
So this object was discovered by a team in the Canary Islands in Europe.
When it was discovered, the observations were directly sent to the Minor Planet Center, and then we publish everything. The role of the Minor Planet Center is to distinguish what is known and what is not known. We define them as a complete new object. And so in the following couple of hours, a lot of observers from all over the world that start observing it. And then it was like a really large impact probabilities, which means it could impact the Earth.
Over a period of a few days, it was had a high impact potential 3 years from the discovery date.
And originally, it had a decently high probability of hitting Earth at its first discovery, and then it was followed up and the probability went up.
And that this impact probability stayed high even if people were sending more and more observations, which means that the path on which the asteroid was really towards the Earth.
2023 DZ2 was a significant asteroid. That kind of close approach to the Earth of a rock that size might only happen a handful of times per century.
And then eventually it turned out that it was coming really close, but it wasn't hitting the Earth.
Other observations had been made to take 2023 DZ2 off the risk list, so that was a good thing.
Suddenly, the probability of hitting Earth goes down. And that's because the more points you gather, the better refined your orbit can become.
At NASA, we thought this would be a good opportunity to launch an observing campaign in coordination with the International Asteroid Warning Network to try to get the worldwide community together to gather observations about physical properties of an asteroid and turn that around quickly.
So we essentially had a very short 5-day campaign where we had to reduce the impact risk by observing the object and collecting more positions along its orbit, understand its rotation period, understand its composition, try and observe it with radar to get some physical information like the size and volume, and try and input all this information in an impact hazard model to see what would be the impact on the ground. So we were able to pull all of this stuff off within a matter of 5 days.
We took this real-world opportunity to exercise the whole system and campaign that would be done if a potential impactor was found.
In case we were ever faced with a situation where we needed to do that, to measure the properties of an asteroid during a short window in a coordinated fashion with the worldwide community.
So we used the Goldstone radar to observe it, and we managed to obtain images with the resolutions of under 4 meters on this asteroid, which showed that it was an irregular body. It was spinning extremely rapidly. Based on the visible extents in the radar images, we could tell that the asteroid was somewhere about 30 to 40 meters, so a bit smaller than what we could estimate using just the visible. It was an important target to practice working together, to exercise the systems in order to refine the orbit and improve the characterization of the asteroid.
So my students and I, we observed this object using telescopes, one on campus. We also used the NASA Infrared Telescope Facility, which is on Mauna Kea, Hawaii. It is one of the few telescopes in the world that is capable of telling what asteroids are made of. So we try and do geology with the telescope. We're trying to do prospecting, trying to understand what minerals are there on these asteroids, and using those mineral signatures, kind of the spectral fingerprints, to identify what fingerprint matches with those of meteorites that we have in the lab. So that's what we were trying to do with DZ2.
So this is the 2023 DZ2.
This is the motion, this is the object that's moving there is DZ2, correct?
Yeah, so you can see it moving through the star field.
Star field, and that's the spectrum, the visible spectrum right next to it, the first order visible spectrum.
Yeah.
So in the end, what we assessed about DZ2 was that it was much brighter than we expected, because when an asteroid is discovered, we don't know how bright or dark it is. So that sets a range in size, okay? You can slowly narrow down the size depending on more characterization information. So if you have radar, that gives you a very accurate, diameter, pretty close to the final thing. If you have thermal infrared measurements, you can constrain the observations. So you can constrain the diameter for that. But you also have composition. Composition tells you something about how bright the object is. So that gives you an additional piece of information. So no one technique gives you the ultimate answer, but complementary sets of information from different telescopes, different techniques, kind of let us converge to one answer. In the case of DZ2, what we've done is with the IRTF, we spectrally characterized. We looked at the light reflected off DZ2 in different wavelengths. And in the infrared, in the wavelengths we cannot see, but rattlesnakes can see, kind of like heat-seeking stuff. What we see is a unique spectral signature for a specific mineral that is only found in this particular type of meteorite called auberites. And we have a few of those in our collection, both that fell on the Earth, fell in Antarctica. So here's an example of it. This is an auberite. It's essentially white, okay? It's reflecting 60 to 70% of the light. What we do is that take this meteorite, crush them into a powder, and put them in a lab spectrometer to get the spectrum of this meteorite. In other words, how is light interacting with it at different wavelengths. So what we do here is that we take a sample and then we crush it and we have it, being observed by the spectrometer that we have it here. Instead of the sun, we have a light source that is reflecting, off the sample. And we're collecting visible near-infrared spectra of that sample that we have. Spectrum is nothing but light split into many wavelengths. And using that spectrum, we compare the same thing we get from the NASA Infrared Telescope. And we can try and match, the spectrum of the meteorite in the lab versus the telescopic spectrum, off the near-Earth object itself. And by taking this spectrum and comparing to the one that's coming off the telescope, off the near-Earth asteroid, we should be able to compare and tell what the near-Earth asteroid is made of. Because it was so bright, you don't need the object to be that big. So it ended up being smaller than what we expected of the size range. And because if it's smaller, hopefully we pray that the atmosphere takes care of it and we won't have much impact on the ground. So that's what ended up happening, is that we managed to nail the composition of the object very well using the NASA Infrared Telescope facility.
So 2023 DZ2 was a really interesting example of planetary defense working on an international scale. So it's really a resounding success in multiple organizations across the planet coming together. And the fact that we were able to discover it, characterize it, determine it was a risk, and then remove that risk all before it passed close to the planet was a pretty amazing feat.
Let's say we do find something that poses an impact threat to Earth. What next?
The day is coming when Earth will get impacted.
The dinosaurs went extinct because they didn't have a space program. We do have one.
We can. So why stop there?
Ten.
9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of the Falcon 9 and DART on NASA's first planetary defense test to intentionally crash into an asteroid.
We're embarking on a new era of humankind.
We're doing this mission to prove that we can deflect an asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, even then, we might still miss.
For the first time ever, humanity has changed the orbit of a planetary body.
NASA confirms that DART successfully changed the targeted asteroid's trajectory. Now, this is a watershed moment for planetary defense and a watershed moment for humanity.
As was demonstrated with the DART mission, if an asteroid were ever discovered that could pose an impact threat to Earth, and we do have the capability to deflect an asteroid in space and to change its orbit.
Once we've found an object and determined that it could be an impact threat to the Earth, what do we do to mitigate it?
Eventually, we have to be ready to nudge an asteroid off its course.
NASA's recently demonstrated a particular type of mitigation technique that we call kinetic impact.
In case there was an asteroid coming towards Earth and you're there, you can actually stop it. I mean, that's kind of fantastic.
Our double asteroid redirection test, DART, was a demonstration of using the kinetic impactor technique.
The idea is pretty simple. You basically just take a spacecraft and you run it into an asteroid and bump it out of the way.
What? You think science fiction, but this is real.
Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid.
Its main goal was to go to an asteroid with its moon, to hit the moon, and see how much it changed the orbit of the moon.
The moonlet Dimorphos, which orbits the asteroid Didymos, in order to change Dimorphos' orbit and show that we can deflect incoming asteroids if we need to.
DART will only be changing the period of the orbit of Dimorphos by a tiny amount, and really that's all that's needed in the event that an asteroid is discovered well ahead of time before it might impact Earth.
In space, just a little bit is just enough to make an asteroid actually miss us. So behind me, you see the spacecraft.
It's really cool to see it coming together in real life.
It is fantastic to see it in real life.
To see it turn from ideas into real pieces that are going to go into space.
The solar arrays will actually roll out to 28 feet in length.
Once the solar arrays are deployed, it's going to be the size of a school bus. As the solar array opens out, it's going to swing out in this direction. To me, the most important thing and the most exciting thing is all the technical challenges. My job was primarily to make sure all the systems on the spacecraft work together. On top, you see the next sea thruster. Over here is our star tracker, and then over here is our high gain antenna. My job is to make sure we launch. My job is to make sure we're able to receive data back. My job is to make sure we hit. There's Draco on the bottom of the spacecraft, as well, of course, as integration and test. The asteroid's only 2 football fields in size.
We're flying at over 6 kilometers a second.
30 days out, we see 1 pixel on our field of view.
You can see Didymos and Dimorphos as 1 point of light.
About 4 hours out, our spacecraft becomes autonomous.
And then that's where everything gets really exciting.
You actually are seeing impact.
The algorithm has to identify and hit the target in the field of view of the camera. And so you could just imagine if it was a human being joysticking this. Because we don't know for sure what the asteroids look like, our simulation gives us the capability to use different asteroid shapes and asteroid objects to see that our SmartNav algorithm performs against all these unknowns.
Astronomers are going to measure how much DART changed Dimorphos' orbit using ground-based telescopes all over the world. These curves show the brightness change due to Dimorphos moving in front of and behind Didymos. We can tell how quickly Dimorphos is moving around Didymos. We make these measurements before DART arrives, and then this is the same technique that we'll use after the impact to determine how much we've changed the orbit by.
This is Lowell Observatory. Lowell is one of many observatories around the world that will be observing the DART impact, NASA's first ever planetary defense test mission, to see how much a spacecraft impact can deflect an asteroid in its orbit. This is where Pluto was discovered, and we are still doing research in all areas of astronomy today. So let's go check it out. This is the Pluto telescope, the telescope that was used to discover Pluto almost 100 years ago. So here we are at the Clark Telescope. This is where Percival Lowell sat to observe Mars. Let's head on over to the Lowell Discovery Telescope, about an hour south of Flagstaff, which is where we are going to be collecting data for the DART mission. And the reason we're all the way out here in the middle of this forest is that we have really dark skies here. And this is the Lowell Discovery Telescope. This is what a 4.3 meter telescope looks like. This is what we will be using to study Didymos and Dimorphos in the days and weeks after DART impact. The DART spacecraft will be hitting an asteroid called Dimorphos. It's special because it's a binary asteroid, which means a satellite around a larger asteroid called Didymos. And DART will actually be hitting Dimorphos. And what we will be measuring is how much DART changes the orbit of Dimorphos around Didymos. And so this is an important test for planetary defense mitigation strategies in case we ever have to do this for real. The Lowell Discovery Telescope is one of many telescopes around the world which will be used to study Didymos and Dimorphos. It's really a global coordinated effort. And what we're looking at here is a large 4.3 meter primary mirror that's in the middle of the telescope tube here. Up at the top is a secondary mirror. The secondary mirror up top there is what is focusing the light down onto the instruments and allows us to take images with the camera that's located down at the bottom. This is maybe one of my favorite hidden rooms at the telescope. We're like standing inside the telescope, underneath the telescope, 100 tons above your head, held up by this and this, which is cool. It's sort of, as you can see, the highest peak around here, just over 8,000 feet. I come up here for sunset. Because, sun's setting right there. It's perfect. For DART, we're going to be collecting images of the night sky. And typically an observer would be here in front of one of these consoles, controlling the instrument and taking images like these as they're coming in off the telescope. DART is really a sort of before and after experiment. We need to understand the system before the spacecraft intentionally impacts, and then we have to understand what the outcome of that impact event is. As we watch from the Earth, Dimorphos will pass in front of Didymos and behind Didymos. What we will be doing with those images is measuring the brightness of Didymos in those images and looking at how that brightness changes. And those dips in brightness allow us to measure when these eclipses happen and measure the orbit period of Dimorphos. And so you have essentially a fixed star field here. All the white dots are stars of different brightness. And moving through this field is Didymos and Dimorphos, which again, we can't distinguish them as discrete points of light, but we have that small object moving through the field of view. So after impact, we will then be able to go back and start observing intensely, looking for those mutual events, those eclipse events of Dimorphos passing in front of and behind Didymos. And on each one of these frames, we're measuring the brightness to assess whether or not it's undergoing one of these events where Dimorphos is passing in front of or behind. This is such a cool experiment. It's such a singular experiment. Using the ground-based telescopes like this one and others around the world to watch the systems and see how it's affected by this impact event, because that's really what's going to give us the answer to what did DART do at the time of impact. And that will be exciting to see how that evolves over the days and weeks following that impact.
Good afternoon, everybody. 2 weeks ago, we conducted humanity's first planetary defense test.
The team has measured that the orbital period of Dimorphos has changed.
Astronomers have been using telescopes on Earth to measure how much that time has changed.
These telescopes have been observing this system nightly. And that's what you see going across here on this graph on the top. Just this nightly telescopic data, night after night after night.
And it resulted in moving an asteroid and actually changing its orbit by a few millimeters per second. Now that doesn't sound like a lot, but acting over a long period of time, it could be enough to help move something out of the way of the Earth, should we ever need to do so.
It was expected to be a huge success if it only slowed the orbit by about 10 minutes. But it actually slowed it by 32 minutes.
The whole world has been watching this.
Wow, I mean, what an exciting day for the DART team. In case you're keeping score, humanity 1, asteroids 0.
Go DART! The dinosaurs are made completely extinct by an asteroid impact so many years ago. Here we are, we can actually do something about it. I think this is just wonderful.
There are times, in a year or in a decade when you're in awe of humanity, you know what I mean? Despite everything that happens in the world on a day-to-day basis in a news cycle, there are times when, human beings kind of come together to do great things. And I think for me personally, DART was one of those moments where you're just in absolute awe of humanity. Here we are taking a spacecraft and flying it, hundreds of millions of, kilometers away and hitting an object with that precision. And it all happens in a blink of an eye, you know what I mean? It was not a long mission, and I think I'm very, very proud of my colleagues who managed to pull that off.
It demonstrates how far we've come as a species in the last few centuries even. From the first rockets launched into outer space, the first asteroids being discovered, to the ability to realize what threat asteroids pose to the planet, and now the capability demonstrated to send a spacecraft to an asteroid that's in orbit around the sun and show that we have the capability, if we have enough lead time, to alter its orbit. That to me was just a fascinating moment in human history.
Oh yeah, I did watch it. I was like, it was super cool. I did watch the DART mission.
Yes, I have watched the DART impact. It was pretty amazing.
The last video that they were showing live, and then you saw everything up until to the last moment. I thought that was such a big achievement. It's something like people work on it for so long, and it proved that we can do it.
The DART Impact Day was one of the most exciting days in my career. We watched the impact here at JPL. The impact was bigger than I had expected, but I was also excited because we had an observing run for observing Didymos just about 11 hours after impact, and it would be the first opportunity to see how much of an effect the impact had. Didymos was all I was thinking about the whole day. I couldn't sleep. The observing run started at about 3 a.m. that night, and we had our first echo of Didymos after impact. We weren't expecting to measure the deflection that night, but the echo was off from where it should have been if there was no DART impact. And I couldn't believe my eyes. I was like, either there's some problems in the measurement, or this is a real detection just 12 hours after impact. So this was the first Goldstone radar detection of the effect of the DART impact on the orbit of Dimorphos. The yellow circle, it circles the location where the echo from Dimorphos should have been had there been no DART impact. But then the red is circles the echo of Dimorphos, which you can see as this white dot here. And you can see it's quite far away from where it should have been without the impact.
And it just gave it a small nudge. But if you wanted to do this in the future potentially, it could potentially work, but you'd want to do it years in advance. Warning time is really key here in order to enable this sort of asteroid deflection to potentially be used in the future and is part of a much larger planetary defense strategy.
The DART mission was the first kinetic impactor demonstration.
It was a successful demonstration of that technique. There are also other possible techniques.
If you do find one that is coming, definitely, there are several options.
There are different types of mitigation, and they actually depend on when you discover that the object is going to impact.
Well, one of the most important things we can do to ensure that mitigation actually works is we need to provide time.
Time is your best friend.
I have time to build a spacecraft, go to space, analyze the object, try to understand what type of physical properties this object has.
Then what we call the reconnaissance mission, to fly by a rendezvous so that we have a better understanding of what the asteroid is, such as the size, the mass.
Chemical composition, for example, it is a solid rock, as it has boulders, something like that. And then you want to know its orbit in a very accurate way because you want to track it down and like go straight on it.
The next step is to figure out the mission that could potentially deflect the asteroid.
There are other techniques, though, that still remain to be tested for asteroid deflection.
A gravity tractor, for instance, where you just have a spacecraft of some significant mass, station keep with the asteroid in the right position, and the mutual attraction between the two objects will allow the spacecraft to slowly tug the asteroid off of the impacting trajectory. Another technique might be an ion beam deflector, where you've got a spacecraft that turns its ion engines onto the surface of the asteroid, continuously bombarding the surface of the asteroid does create a pressure on its surface and therefore a force that changes the velocity of the asteroid. Of course, all the Hollywood movies like to use nuclear explosives. It's very dramatic and exciting, but we wouldn't blow the asteroid up like they do in the movies. You detonate the device, bombards the surface of the asteroid with heavy radiation that causes the surface material to vaporize and jet off and creates instantaneous rocket engine, so to speak, and shoves the asteroid.
Really, the goal at NASA is to find the asteroids years or decades in advance that could pose an impact threat to Earth. And then you have the gift of time to address possibly not having that impact happen at all. NASA is just one piece in the puzzle. NASA has its role as the information gatherer from space and conveying that information to other agencies.
Every piece of the puzzle must rise up to the occasion and perform seamlessly. To do that, we have to practice.
NASA also participates in interagency exercises with many others across the U.S. government to step through a situation where an asteroid is discovered so many years ahead of time. Here's the type of information that is known about it. Here are the possibilities of what could happen next.
Good morning, everybody. Thank you for coming. It's been a pleasure. This is our 5th exercise.
Welcome to the 5th Interagency Planetary Defense Tabletop exercise.
This exercise is incredibly important to bring together the world experts and decision makers.
ESA Planetary Defense,
National Space Council,
FEMA,
NASA headquarters,
U.S. Space Command,
the Department of State,
to better prepare us for what is an inevitable future asteroid impact. We know it will happen. We just don't know when it will happen.
You know, really this exercise focuses on is how we plan and coordinate our activities in response to a potential impact, for it all to come together into a plan on how we save the world.
And with that, I invite you all to open the blue envelope in your folder. And what you have in front of you is a notification from the International Asteroid Warning Network about this hypothetical scenario of a potential asteroid impact for the near-Earth asteroid 2023 TTX.
At this point in the scenario, the impact probability of the asteroid is 72%, as calculated by NASA JPLC NEOs and by the ESA NEO Coordination Center. The impact date would be the 12th of July, 2038. The potential impact locations would span a corridor from the South Pacific across North America, the Atlantic, the Iberian Peninsula, the Mediterranean coast of Africa, Egypt, to the coast of Saudi Arabia. Now, the size of the object based on observations from the ground, it's highly uncertain based on the brightness and the unknown surface reflectivity, the coloring of the asteroid, and so it's most likely estimated to be in the range of 100 to 320 meters based on what is known about asteroids, but potentially at the extreme range of 60 to 800 meters in diameter.
All right, so the next critical factor to consider is, of course, how many people could be affected by these different damage sizes along the different impact locations.
It's certainly regional to country scale based on that size range.
For asteroids in this general size range, the primary hazard is going to be local blast and thermal ground damage, and the larger sizes could also cause tsunami. So overall, the average population risk is around 270,000 people among all the potential Earth impacting cases. And then, of course, there's still that 28% chance that the asteroid could swing by Earth and miss us entirely.
We have filled out the uncertainty in 2038 with a bunch of white dots. And we really don't know which of those white dots is the real asteroid. And so we simulate virtual asteroids and we just run them all towards the Earth. The current situation is that we don't know where it will hit. We just know that it will hit along this line.
For this exercise over the next 2 days, we're going to stay frozen in time, right here, right now, 14 years ahead of the asteroid impact, and figure out what do we do with the information that we have now.
Disaster preparedness planning, international space response, information sharing, and public messaging.
So the challenge now is to figure out how do we respond and prepare for an uncertain event like this where we're not sure what could happen, but the potential consequences could be quite catastrophic.
This gets at sort of what we were hinting at there, starting to talk about not just what the threat is, but what we could potentially do about it.
The good news is this asteroid impact may be preventable. We have at least 3 technologies that we can consider for this, and they have different physical effects. So the first is kinetic impact, which is like the DART mission, where a spacecraft impacts the asteroid to change its speed very slightly. The second is an ion beam, where you use a controlled electric thruster to slowly push or pull on the asteroid and change its speed. And then finally is a nuclear explosive device, where you literally boil off part of the asteroid in order to change its speed. And we also need to know the physical properties of the asteroid, because all of these methods, whether or not they work and the specifics of how you would design them, are tailored to the specific asteroid properties.
Through forums like this one today and tomorrow, and bringing together all of you, the world experts, we can tackle the detection and characterization of asteroids, ways to improve coordination among allied nations.
That's why we want to exercise all of these capabilities now and not wait until then.
We took this opportunity to exercise the whole system and campaign that would be done if a potential impactor was found.
Planetary defense is a team sport.
Asteroid impacts are a shared risk, and so we really need to work as a team.
It's really important that we have a global effort to try to understand the problem.
No one nation can independently save the world in case of an impending impact.
It's a fantastic community.
I'm part of a global team of planetary defenders.
Very proud to be part of that planetary defense family.
It not only protects Earth today, but provides protection for the future.
Greenland, a massive ice-covered island in the northern Arctic. A land of pristine waters, enormous glaciers, and ancient geology. And for some, the site of a hotly contested claim of the oldest signs of microbial life on Earth.
I mean, it's always when I go see some rocks and outcrops in the flesh, it's so much more eye-opening and informative than it is to read about in the papers. And absolutely the case with this one, and I came to see them after that paper was published.
Meet Dr. Abigail Allwood, astrobiologist at the NASA Jet Propulsion Laboratory. Dr. Allwood is here in Greenland to investigate recently published findings of possible stromatolites, or microbial fossils, dating back to 3.7 billion years ago.
I very much doubted that interpretation, and I thought, well, we need to do two things. We need to put a paper out, and secondly, we need to do a workshop and bring a lot of people out here to also see what their opinion is, reach some sort of a consensus on what the right interpretation was.
Extraordinary claims require extraordinary evidence, and a finding like this requires further investigation. Dr. Allwood has gathered a team of astrobiologists and will now travel by helicopter into the wilderness of the Ishua Greenstone Belt.
So we're out here to study an outcrop that there is some controversy over. There is a group of authors that has made a claim that there are biosignatures in the form of stromatolites in these rocks. And there's another group of authors, I happen to be one of that other group of authors, that has refuted that claim. So we're out here in Greenland to study those outcrops in more detail and to try to get a sense of the geology that surrounds those potentially stromatolite-bearing outcrops and try to get a sense for what the ancient environment looked like at the time that those rocks were forming. The claim was such a big deal because if it proves to be true, then this pushes back the earliest signs of life in Earth's geological record by a couple of 100 million years.
It means that the window of opportunity for life to emerge doesn't have to be very big. You know, literally, as the last bombardment is occurring, that you can say that life can take hold. At least our one example that we have that life took hold. Go to Mars. It means that it only also had to maintain its conditions, its sort of cradle of life, its opportunity for life to emerge for that short period of time. It didn't have to sort of maintain it for a couple 100 million years longer.
And when you go back to those very old rocks, they're usually altered and deformed, and it's very difficult to find those signs of life. But those are also the most interesting rocks to look at because we don't know when life originated on Earth, and we don't know what that earliest life was like. So the record that we have from geology is in these rocks that are very difficult to interpret.
I wonder which way I'm going to put it.
Sampling here in Greenland is, it's not all that different from sampling anywhere else. A geologist's tools are kind of the same no matter where you go. You need a hammer, a chisel, a little, hand lens to look at the rocks up close, field notebook, camera, and, you record your observations, and when you think you've zeroed in on a piece of rock that might be worth taking back to the lab, you get your trusty rock hammer out and just start banging away until the sample comes out.
When we're looking at rocks, trying to understand if they preserve evidence of life, we look for things in the rock that cannot form without the influence of life. They can change the chemistry, and they can actually change the shape of the ground. And they can make things like peaks and domes that are sometimes unique to the biology.
Again, I think here what you need to do is look at the context of the rocks around those stromatolites and try to get a sense for what that geology is telling you.
This is our sample here. From the outcrop. We've got that more sort of cut and polished face there. And if it was really a cone-shaped structure, then you shouldn't see it on the back of the sample. You shouldn't see it in the back of the hole there. It's about 14 centimetres depth hole. You're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. Got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front, it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what happened in the rocks. Part of making that story, though, is understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.
The rocks that we're looking at here in Greenland are similar, if not identical, in age to the rocks that we're going to be exploring with the Mars 2020 rover. We'd like to think that we can use the lessons that we take from studying the Earth's geological record and apply them when we start exploring the geology of Mars.
One of the really interesting things about searching for life on other worlds is, as a scientist, I have to actually, when I'm looking for life anywhere, I have to actually have a model of what I'm looking for to help guide my observations. And so by looking at these places that are very difficult to interpret on Earth, we get that practice and experience of how do we look at something and what are the questions that we need to ask and what are the observations we need to take to be able to answer them.
Any claim that is made about a biosignature on Mars is going to be debated. So I think that this workshop gives us an opportunity to exercise our ability to have civil disagreements over matters of scientific importance, because I think we're going to be doing much of that, with the data that comes back from Mars as well.
I think seeing the rocks in the flesh is just so important. Can't do that for many people, so I think the next best thing is to try and recreate that in a virtual terrain sort of field trip kind of thing. That's what we're trying to do.
So OnSite is an application that we developed for the Mars Science Laboratory mission to help the science team that works with the Mars rover understand the context of the environment around the rover.
And it provides scientists the ability to basically meet on Mars. So it's taking Martian data down from the rover and using photogrammetry to stitch it together to create a 3D model of the outcrop. And then scientists involved in the mission and engineers as well are able to use that 3D model, enter the terrain and make decisions with a much better understanding of the context. We're also using LiDAR imagery out here, which is something not available on Mars. So that's using a laser scanner to basically three-dimensionally scan outcrops and get higher fidelity data so that we can get some very accurate information.
Yeah, so this is the map of the primary outcrops and the laser scans. This is the A outcrop here. There's the flag, there's the cut of the rock, and the other cuts.
Now on Mars, it's a different scenario because we're limited to the instruments on board the rover. The rover doesn't have LiDAR. It'd be great if it did. So all we have are the 2D images to work with. 3D reconstruction from 2D images has been part of the Mars missions all the way back to Pathfinder in the late 90s. But it's always been on a per image basis from one rover position. So one of the innovations in OnSite is we started combining rover imagery from multiple rover positions. So if the rover's parked next to a rock and the next day you drive around the rock, you can take imagery from those two positions and get a more complete model of that rock than from any one position on its own. And the holy grail of this is to take all of the rover drives from landing to the current position, register them all together so you could walk from the landing site to the current rover position, seeing high-quality 3D imagery all the way. So OnSite was started in the context of the Mars rover missions, but the capability that OnSite and tools like it provide is really, it's virtual presence and situational awareness in an environment that's hard to visit. Mars is an extreme example of that, but where we are today in western Greenland is not quite as hard to visit as Mars, but it's certainly not easy. So you can imagine geologists going into the field to these remote locations and bringing back not only their written field notes and photos, but a 3D capture of the environment that becomes kind of an immersive field notebook that they can revisit, they can share with their colleagues and with the public and help to communicate what that environment is like in a way that's really hard to get without actually being there in the field. So I don't think this technology ever really replaces a human in the field. Whether or not humans will go to Mars is not my expertise. But if and when humans do go to Mars, only a select few will go to Mars. But with this kind of technology, they can bring along experts from Earth to extend their knowledge and share that experience with the public.
It's Friday, August 8th, and we're joining you today from SpaceX in Hawthorne, California. We're following along with the Dragon Endurance spacecraft as we await Crew 10's departure from the International Space Station. Right now, we're expecting that process to begin shortly after 3 p.m. Pacific and 6 p.m. Eastern. I'm Ronnie Foreman, a senior sales manager here at SpaceX.
And I'm Anna Schneider with NASA Communications. It's great to be here.
It's great to have you here, Anna. And of course, thank you for everyone tuning in to watch us live with our coverage today of Dragon completing its 10th crew rotation mission to the space station through NASA's Commercial Crew Program. Crew-11 arrived on station on Saturday, August 2nd at 2:27 a.m. Eastern, and they will be taking over for Crew-10, who are now headed home.
That's right, Ronnie. Crew-11 launched just last week on Friday, August 1st at 8:43 a.m. Pacific, 11:43 a.m. Eastern from Launch Complex 39A at NASA's Kennedy Space Center in Florida, with NASA astronauts Commander Zena Cardman and pilot Mike Fink, JAXA, or Japan Aerospace Exploration Agency astronaut and mission specialist Kamiya Yui, along with Roscosmos cosmonaut and mission specialist Oleg Platonov. The crew has since spent a few days in space, with those days docked to the space station being a handover period where they learn to live and work on station from the departing crew. Now, the returning Crew-10 members today are NASA astronauts Anne McClain and Nicole Ayers, along with JAXA astronaut Takuya Onishi and Roscosmos cosmonaut Kirill Peskov.
Right now, the crew is currently suited inside Dragon, and both the Dragon and station hatches are sealed in preparation for departure. Once Dragon departs the station, the crew's flight home is expected to last around 17.5 hours. Shortly after separation, Dragon will use its Draco thrusters to carefully move away from the station and complete a phasing burn that will prepare it to re-enter the Earth's atmosphere. Following phasing, Dragon will complete deorbit, re-entry, and splashdown. During our deorbit sequence, several events will occur, including trunk separation, closure of the nose cone, a deorbit burn, deployment of the drogue and main parachutes, and finally, splashdown. And of course, like all of our mission with Crew-10 so far, Mission Control, SpaceX, and of course on the big loop connected to Houston, we'll be monitoring their progress all the way. You've got a great view of Mission Control at SpaceX here, but we'll hear call-outs from Mission Control in Houston here shortly. And of course, Dragon is targeted to splash down off the coast of California tomorrow, August 9th at 8:33 a.m. Pacific, 11:33 a.m. Eastern, where it will be picked up by a SpaceX recovery vessel, and our recovery teams will help to egress or exit the crew from Dragon.
Now, currently on board the space station is the Expedition 73 crew, led by the current space station commander, Sergei Ryzhikov of Roscosmos. Just a few days ago, JAXA astronaut Takuya Onishi handed over command of the space station to Ryzhikov ahead of his departure today, alongside his Crew-10 crewmates. Now, also on board space station is NASA astronaut Johnny Kim, as well as Roscosmos cosmonaut Alexei Zubrytsky, and of course the recently arrived Crew-11 astronauts. Now, just like its approach to the International Space Station, Dragon's departure and deorbit is designed to be fully autonomous, requiring no action from the crew on board. NASA astronaut Johnny Kim has helped the crew members prepare for today's departure and will be watching from the cupola, but the prime departure monitoring role falls on Anne McClain from inside Dragon. Mission Control in both Houston and Hawthorne will back them up as we step through today's undocking. And speaking of Mission Control in Houston, let's check in with NASA Public Affairs Officer Rob Navius at the Johnson Space Center in Houston to talk a bit about how the station crew have been preparing to send today's crew home and what we can expect from here until Dragon departs from station. Rob?
Thanks very much, Anna. Here in Mission Control in Houston, the team on console is led by Flight Director Allison Bollinger. She's joined by spacecraft communicator Tess Caswell, who will be talking directly to the crew through that big loop you described, all the way through the exit from the so-called approach ellipsoid, which is the racetrack boundary, after which joint operations will conclude between Houston and your Mission Control there in Hawthorne, California. A short time ago, Bollinger polled her team of flight controllers here and received a go for undocking. Now, the undocking time has been adjusted ever so slightly by just a few minutes to the right. The undocking command that will initiate the retraction of the umbilical between Dragon and the station that has been providing telemetry and electricity to the Dragon Endurance will be retracted. That will then initiate the opening of 2 sets of hooks, 6 hooks per set, that will physically separate Dragon from the International Space Station and conclude its 5-month stay on board the orbital outpost. Once that separation occurs, and it is now targeted, by the way, for 5:15 p.m. Central Time, 6:15 p.m. Eastern Time, that would mark physical separation. Dragon will move away from the forward port of Harmony to a point about 400 meters in front of the station. Then, through a series of departure burns, will move to a point above the station, behind the station, and then will phase away below the station for a 17.5-hour transit to its deorbit burn and splashdown off the coast of California on Saturday morning, as you described. The crew statistics for Crew-10, very impressive. They will have spent 148 days in space at the time of their splashdown on Saturday morning, 146 days of which were locked in and working with the Expedition 73 crew aboard the International Space Station. McLean, Ayres, Peskov, and Onishi will have completed 2,368 orbits of the Earth, a mission spanning 62.7 million miles. And McLean will have totaled 352 days in space during her 2 missions once she returns to Earth on Saturday. Ayres and Peskov, both first-time flyers, will have accrued 148 days, and Takuya Onishi, completing his 2nd flight into space, will have totaled 263 days on his 2 missions. So everything is all set for the departure of Crew-10 from the station. By the way, the delay, the wave-offs, if you will, because of weather over the past couple of days, concluded with a weather briefing this morning, and SpaceX and NASA were both go for undocking with the conditions, lighter winds, and even though there are some low clouds expected at the time of final descent for Endurance to its splashdown point off the coast of California, those conditions are well within limits to allow the undocking today and the return to Earth tomorrow for Crew-10. With that, we'll hand it back to Ronnie and Anna in Hawthorne and stand by for physical separation.
Thank you so much, Rob, and thank you for those updates. Of course, the team will continue to watch and monitor the weather all the way through splashdown and as they make their way through those phasing burns and onto deorbit tomorrow morning. And we heard just a minute ago that the teams were doing their final go, no-go poll. Again, they do all of these checkpoints and sequence all the way up through undocking to make sure all the teams are ready to go. And should for any point they have to wave off last minute for weather, whatever it may be, there's, of course, opportunities down the road.
Yeah, absolutely. And because it does take us time to get back from the International Space Station to our splashdown location, we're monitoring weather not just at the time of separation, but trying to do that forecast ahead to make sure that we're going to have an easy splashdown for our crew, who are coming back from, almost 150 days in space. I want to make sure it's a warm welcome back here in California.
Yeah. And now let's take a moment to go ahead and meet the crew that we're bringing home today before they depart the International Space Station. So first up, we have NASA astronaut Anne McLean, who is your Crew-10 commander. Born and raised in Spokane, Washington, NASA selected McLean as an astronaut candidate in 2013. Crew-10 is her 2nd space flight after launching aboard the Soyuz MS-11 in 2018 and serving as a flight engineer on the International Space Station for expeditions 58 and 59. At the conclusion of this mission, as Rob mentioned, she will have spent 352 total days in space across her 2 missions, completing a total of 3 spacewalks for 18 hours and 52 minutes outside the orbiting laboratory. McLean is a West Point graduate and a colonel in the U.S. Army. She's a highly decorated Master Army aviator and has more than 2,000 flight hours in 20 different aircraft. McLean is also an avid rugby player and a former member of the USA Rugby Women's National Team, and she currently lives in Houston, Texas.
The pilot for Crew-10 is NASA astronaut Nicole Ayres. Crew-10 is her first space flight. A major in the U.S. Air Force and the first member of NASA's 2021 astronaut class named to a crew. Following this mission, Ayres will have logged 148 days in space, completing 1 spacewalk for a total of 5 hours and 44 minutes outside the space station. Ayres is a graduate of the U.S. Air Force Academy.
Dragon SpaceX on the Big Loop. Final reconfigurations for undock are complete and nominal. Ground is go for undocking. Undock sequence start time is 22:10.
SpaceX starting. Copy. Go for undock. Crew has visors down.
SpaceX copies. Visors down.
We heard a little bit of chatter there between mission control here in SpaceX communicating with our crew on board. And we've got confirmation that visors are down. What we're doing right now is getting the crew into their fully suited up, ready to depart configuration, because we want to make sure that for all of these dynamic phases of flight, we have them safely inside their spacesuits. So with that, let's take it back to our crew. We were just discussing mission pilot Nicole Ayers, who is a graduate of the U.S. Air Force Academy in Colorado Springs, Colorado. She has served as an instructor pilot and mission commander in the T-38 Adair and F-22 Raptor, leading multinational and multi-service missions worldwide. She has more than 1,400 total flight hours, including more than 200 hours in combat. Ayers has a twin and was born in San Diego, California.
And this is also the second mission to the space station for JAXA, or Japan Aerospace Exploration Agency, astronaut Takuya Onishi, after launching aboard the Soyuz MS-01 mission in 2016 and spending 113 days in space as a flight engineer for expeditions 48 and 49. Following Crew-10, Onishi will have logged a total of 263 days in space. Onishi received a Bachelor of Engineering in Aeronautical and Space Engineering from the University of Tokyo and soon embarked on a career in aviation with All Nippon Airways in Tokyo. He was selected as an astronaut candidate by JAXA in 2009, and during his stay on the space station, he became the first Japanese astronaut to capture the Cygnus spacecraft in space. Now, when he's not training, Onishi enjoys flying, playing the saxophone, movies, and hiking.
And rounding out our crew, this is mission specialist and Roscosmos cosmonaut Kirill Peskov. Like Ayers, the Crew-10 mission is also his first trip to the International Space Station. After the conclusion of this mission, he will have spent 148 days in space. Before his selection as a cosmonaut in 2018, he was a co-pilot on the Boeing 757 and 767 aircraft for airlines Nordwind and ECAR. Assigned as a test cosmonaut in 2020, he has additional experience in skydiving, zero-gravity training, scuba diving, and wilderness survival.
And it's a great crew that we are bringing home. Of course, now on your screen, you can actually see a look inside Dragon. That's looking over the shoulders of the pilots and commanders. So Nicole Ayers and Ann McLean there in the center. They're all suited up and getting ready for today's departure. Again, we're just over about 10 minutes away from the undock command, and once that undock command is sent, it takes about 5 minutes to then have that physical separation from station, which will then mark the conclusion of their stay aboard the International Space Station as they make their way home to Earth. And just a few minutes ago, when we were introducing you to the crew, we heard some of those comms. Again, those comms were on what is known as the big loop. So that's that integrated communications loop that includes the team here in Mission Control in Hawthorne, as well as the Mission Control team in Houston, along with the space station crew with Expedition 73 aboard and the Dragon crew-10, who is departing today. It basically allows all of those teams to be working in tandem and talking on one integrated communications loop. So throughout today's departure activities, that is where we will be hearing those communications between the ground and the station and crew aboard. And right now, the International Space Station and Dragon are orbiting about 260 statute miles above Earth, crossing the southern Indian Ocean. And we also did just hear a few minutes ago that the teams had pulled go to proceed with today's undocking and departure activities. So again, we are just standing by for that undocking command here in just about 10 minutes.
So again, right now, if you are just joining us, we are standing by for Crew-10's departure from the International Space Station. And the view on your screen right now is looking over the shoulder of the pilot and commander for today's mission, up at the 3 touchscreen displays inside the Dragon spacecraft. Our crew is going to use these touchscreens to monitor their progress as they move away from station, even though the maneuver itself is fully autonomous.
And as we mentioned a few minutes ago, the Joint Flight Control teams did pull go to proceed with today's undocking and departure. And now that the Joint Flight Control teams are go for undock, we are just awaiting that undock sequence to actually begin. Again, the undock command is scheduled to be sent in about 9 minutes at 3:10 p.m. Pacific, 6:10 p.m. Eastern. Once that command is sent, it will take less than 5 minutes for Dragon to separate from the International Space Station, which has been its home for the last 5 months.
At the planned undock time, SpaceX Mission Control will command the undock sequence start, which begins the automatic undocking process we were just talking about. The first step is for the umbilicals to retract. These umbilicals connect Dragon systems to the space station while docked, transferring power, telemetry, and commands between the two vehicles throughout Dragon's stay. Once that's complete, Dragon will unlatch itself from the space station by releasing the 12 hard capture hooks in 2 separate phases, which Rob was telling us about while he was with us a couple minutes ago. All that combined takes roughly 4.5 minutes. And then Dragon will be ready to depart from station and begin to move itself further and further away using the Draco thrusters on board.
And Dragon's initial departure from station is a little bit different from other docked vehicles like the Soyuz that rely on springs to push them away from the docking port. Dragon will actually execute 2 short thruster firings called undock burns, and that is what physically separates Dragon from the International Space Station. Those thruster firings use a combination of the 12 Draco engines around the base of the spacecraft, with the first breaking any stiction between Dragon and the docking port, and then the second slowly backing the spacecraft away from the station's Harmony module. And again, Dragon is currently docked to the forward-facing port on the Harmony module. Crew-11 docked last Saturday to the space-facing port. And following that physical separation, which we are expecting at about 3:15 p.m. Pacific, 6:15 p.m. Eastern, we will have Depart Burn 0, which is the first of 4 departure burns to begin moving Dragon further away from the space station. That initial departure burn, Depart Burn 0, will then be followed by the second departure burn about 5 minutes later, and that will help move the spacecraft beyond the keep-out sphere. The keep-out sphere is an invisible 200-meter line centered on the space station, and it is one of several safety zones set up to govern spacecraft arriving and departing from the International Space Station. Before moving into the keep-out sphere, spacecraft have to be configured where they would not cross the imaginary boundary for at least 4 orbits, even if the spacecraft lost all maneuvering. And then after that, about 13 minutes later, today that would be around 3:34 p.m. Pacific, 6:34 p.m. Eastern, Dragon will then exit what is known as the approach ellipsoid. Again, it's another imaginary shape, this time a 3-dimensional ellipsoid measuring 4 kilometers by 2 kilometers by 2 kilometers in the same family as the keep-out sphere. One of the key differences with the approach ellipsoid is that vehicles outside of it have to be on what we call a 24-hour safe pre-drift trajectory, which means the spacecraft would not cross into the approach ellipsoid for at least 24 hours, even if it lost all maneuvering. Again, we're expecting the call for the undocking sequence to begin in about 6 minutes. And then after that happens, it'll be about 5 more minutes before we have physical separation of Dragon carrying Crew-10 away from the International Space Station to conclude their mission.
Just had a shot a second there of our crew on board working through some final checklists, preparing for that undocking sequence start.
And all throughout today, there have been a lot of procedures that they've had to work through. Before we started today's broadcast, the crew had to work through hatch close procedures, and then they got suited up and completed some leak checks. They also depressurized the vestibule, which is the area in between the Dragon hatch and the space station hatch, which prior to Crew-10's docking back in March would have been exposed to the vacuum of space. Now, of course, after they undock today, that area will then be re-exposed to that vacuum of space. And during their mission, they conducted quite a bit of science. They contributed to more than 200 different microgravity science and research experiments during their time aboard the International Space Station. And the International Space Station will actually mark a very important milestone this year. It'll be the 25th year of continuous human presence aboard the orbiting laboratory. And during that time, over 4,000 different experiments have been conducted in that unique environment.
I'm always struck by when we do these webcasts talking about the expedition numbers of our crew, how many different astronauts have been on board station. And of course, today is the completion of the 10th crew rotational mission as part of the commercial crew program. And of course, our 10th Crew Dragon mission to the International Space Station as well. For those of you just joining us or have not watched an undocking before, in the lower left-hand corner of your screen now, you have the range and rate available so that you can help monitor along from home, just like we're monitoring here from Mission Control. The range tells you about how far away from the station we are, and the rate is the speed at which that distance is changing. So we're looking for both to increase as we move through these carefully planned maneuvers as we go through our separation, phasing burns, and ultimately head towards splashdown.
And what's really interesting about undockings and dockings is that both vehicles are actually traveling at about 17,000 miles per hour. So if you think about it, the relative rate seems small and it seems like they're going so slow when you're watching it on TV, but it's really, they're going very fast, and they orbit about 260 statute miles above Earth. So as Dragon makes its way back to Earth, it of course has to lower down so that it can re-enter Earth's atmosphere, again targeting that splashdown early tomorrow morning around 8:33 a.m. Pacific. And we're now just about 3 minutes away from that undock command, which will be sent to Dragon from the ground, and that will then command the umbilicals to retract, and those umbilicals provide power between Dragon and the space station, and those were initially attached when Dragon docked to the International Space Station back in March. So then after the umbilicals retract, then we will have those hooks begin to drive open, and that will happen in 2 sets of 6. And then once that happens, Dragon will conduct those 2 short thruster firings to physically separate it from station.
And as you mentioned, this is the same Dragon that docked with crew-10 back in March. Part of our operating procedure is such that the Dragon spacecraft that launches the astronauts is exactly the same one that brings them back home. So while our crew-10 astronauts have been aboard the International Space Station, Dragon has been docked to the ISS as well. And we're using them in that docked configuration, effectively as one vehicle. Their spacesuits are stored inside of Dragon, as are some of those experiments that you were talking about.
And of course, they had to repack some of those scientific experiments to make their way back to Earth. Again, we're about 1 minute away from that undock command. So as we continue to stand by, let's go ahead and check back in with Rob Navius at NASA's Mission Control in Houston.
Thanks very much, you guys out in Hawthorne. Here in Mission Control in Houston, all flight controllers are set for the beginning of the end of the Crew-10 mission and the journey home. That will span about 17 and a half hours from the time of physical separation to the time of tomorrow's splashdown off the coast of California. We're about 20 seconds away from the issuance of the undocking command from Hawthorne. We'll stand by for confirmation of that. All of Dragon Endurance's systems are in excellent shape, as are the systems aboard the International Space Station, as we stand by about 10 seconds from now for the issuance of that undocking command. And execution of the command now has been issued. The first step on the road to separation will be the retraction of the umbilical that you just heard a moment ago. And McLean, the commander of Endurance, acknowledging the issuance of the undocking command, the umbilical being retracted. Once again, this means that Endurance will be on its own in terms of internal power and telemetry, no longer interconnected to the International Space Station.
Umbilical demate complete and nominal.
And the first set of hooks now traveling. 2 gangs of hooks, 6 hooks apiece, will open in sequential fashion. Hook set number 1 followed quickly by hook set number 2. And then the next step will be that 1.5 second pulse of the Draco thrusters, the undocking burn, that will create the physical separation between Dragon and the International Space Station. The Expedition 73 crew, who will be left on board the station to continue the unbroken presence of humans on board the orbital outpost led by Roscosmos cosmonaut Sergei Ryzhikov. He's the new ISS commander, joined by Alexei Zabritsky, Oleg Platonov, Johnny Kim, Zena Cardman, Mike Fink, and Kimia Yui. Takes about 5 minutes from the issuance of the undocking command until physical separation, so we'll be standing by to annotate the exact time and location over the Earth at the point of physical separation that will begin the trip home for Dragon Endurance. We're currently in an orbital nighttime pass. We should be moving into a daylight pass over the southwestern Pacific Ocean a short time from now. The International Space Station traveling from southwest to northeast in an orbit inclined 51.6 degrees to either side of the equator. And the first set of hooks now open, now working on the second set.
First set of hooks, open and nominal.
Second set of hooks now driving. All quiet here in the mission control room, here in Houston, the International Space Station Flight Control Room. Once the undocking is complete and Endurance is outside of the approach ellipsoid, which will end joint operations between us and the SpaceX team in Hawthorne, the Expedition 73 crew will move into a pre-sleep period and a lengthy sleep period overnight and an off-duty day tomorrow. The second set of hooks now open, standing by for undock burn number 1. Dragon and the International Space Station flying into an orbital sunrise. All hooks confirmed to be open.
All hooks now open and nominal. Dragon separation.
And we have undocking. Physical separation confirmed. At 5:15 p.m. Central Time, 6:15 p.m. Eastern Time, as the station and Dragon flew 260 miles over Jakarta, Indonesia. And undock burn number 2 has been completed. And depart 0 burn now underway. You can see those Draco thrusters doing their thing, opening up an increasingly quicker separation rate between Dragon and the station. Depart 0 burn complete.
Depart burn 0 complete. Performance nominal.
Visiting vehicle officer here reports good trajectory as Dragon Endurance leaves the International Space Station from which it docked 146 days ago. We're about 4 minutes away from depart burn number 1. That'll be a 22-second firing of the Draco thrusters to increase the acceleration of Endurance away from the international outpost. Again, physical separation, undocking occurring at 5:15 p.m. Central, 6:15 p.m. Eastern Time, as Dragon and the station flew 260 miles over Jakarta, Indonesia. And again, we will remain in integrated operations with Hawthorne, California and SpaceX Mission Control until the time that Endurance has exited the approach ellipsoid, which is that 2 by 2 by 4 kilometer invisible boundary, basically a racetrack-shaped oval-type boundary that represents the vicinity of the neighborhood of the International Space Station within which integrated operations are conducted. Anne McLean, Nicole Ayers, Takoya Onishi, and Kirill Peskov beginning the journey home that will culminate with their parachute-assisted splashdown off the coast of California Saturday morning. The track of Dragon in the station will carry it a moment from now across Malaysia and then just south of Manila, the capital of the Philippines. Everything has gone by the book. All of the pre-departure preparations went per the timeline. The undocking was deliberately pushed back a few minutes to gain better visibility, communications, and camera views of Dragon as it departed the International Space Station. We still are headed for a splashdown on Saturday morning at 10:33 a.m. Central Time, 8:33 a.m. Pacific Time off the coast of California. This will be the fourth time that SpaceX will have executed a splashdown and recovery off the coast of California, following in the footsteps of Fram-2, the 32nd commercial resupply mission, a cargo Dragon, and then most recently Axiom 4, but this will be the first time that a California splashdown will have been executed as part of the commercial crew program. We're about 25 seconds away from departure burn number 1. This is a 22-second firing with a delta velocity change of 0.6 of a meter per second to further increase Endurance's opening rate from the International Space Station. That will be followed seconds later by its exit from the keep-out sphere, the first of these two boundaries within which integrated operations are occurring, and depart burn 1 underway.
Depart burn 1 complete. You are go to doff suits per procedure 4.012. Reminder, ground will be deactivating the big loop following exit from the approach ellipsoid.
Dragon now maneuvering.
Dragon crew 10 copies, go to doff suits. To the ISS crew, Expedition 73 Bravo, it was an absolute privilege to cross paths with you. Good luck in the rest of the mission. Godspeed.
Anne, Vapor, Talk, and Kirill, thank you for your wishes. We wish you fair winds and following seas. It's been an honor for all of us around the world to support you as you lived and worked on the International Space Station. We cannot wait to welcome you home to the blue skies of Earth.
Endurance Commander Anne McLean exchanging words with
station on a big loop. Fair winds and following seas. It was a huge honor to work with you all. We're going to miss you, and we can't wait to see you back on Earth.
Likewise, Johnny and the rest of the crew, have a great mission.
Again, Endurance Commander Anne McLean wishing all the best and a big vote of thanks.
Dragon and Station, Houston on the big loop. Dragon has exited the keep-out sphere.
And as you heard, Endurance is now outside of the keep-out sphere. The next milestone will be coming up about 11 minutes from now, and that will be the approach ellipsoid exit to conclude joint integrated operations. And you heard those words from spacecraft communicator Tess Caswell here in Mission Control, as well as NASA astronaut Johnny Kim, who remains on board the station until early December as part of the Expedition 73 crew. So with Endurance well on the way on the first leg of its journey home that will culminate with its splashdown off the coast of California Saturday morning, we're about to conclude joint integrated operations with Hawthorne here in Mission Control in Houston. And so with that, we will toss it back to Ronnie and Anna at SpaceX Mission Control in Hawthorne, California.
Thanks, Rob. So as you mentioned, we are now waiting for Dragon to exit the approach ellipsoid, or AE, which is another imaginary shape, this time a three-dimensional ellipsoid, measuring 4 kilometers by 2 kilometers by 2 kilometers. As an easy visual, that's roughly like the shape of a football or maybe a rugby ball, which is appropriate given that our commander today is a rugby player. And it's in exactly the same family as the keep-out sphere for operational purposes. One of the key differences with the AE, though, is that vehicles outside of it have to be on what we call a 24-hour safe, free drift trajectory. That means that the spacecraft would not cross into the approach ellipsoid for at least 24 hours. Again, even if it lost all maneuvering for that call-out once we hear confirmation that Dragon is outside of the AE.
And then after the Dragon spacecraft crosses the approach ellipsoid, as Rob mentioned, joint operations will end and responsibility for the spacecraft will be handed back to the SpaceX flight control team here in Hawthorne, California. Again, everything continuing to look good with today's departure for Crew 10 from the International Space Station. Dragon is now just under 400 meters away from the International Space Station. And to recap, the hatches between the International Space Station and Dragon were closed earlier today around 1:04 p.m. Pacific, 4:04 p.m. Eastern Time. And since then, the crew has settled in to begin their 17.5-hour journey back to Earth. The joint NASA and SpaceX teams then pulled go to proceed with Undock. Undock was delayed by
SpaceX third and ComSec and handheld Microsoft.
I have you loud and clear on the cabin mic on the big loop.
Okay, we can hear you loud and clear.
And those comms there were with the core or the crew.
SpaceX Dragon, for com check on Dragon to ground.
I've got you loud and clear on Dragon to ground. How me?
Okay, same. Thanks.
Again, those comms there were between JAXA astronaut Takuya Onishi and the core, or the crew operations resource engineer in SpaceX Mission Control in Hawthorne, just behind us. And again, to recap a little bit, the undock command was sent around 3:10 p.m. Pacific, 6:10 p.m. Eastern. This was then followed by umbilical retraction and hooks opening, with that physical separation then taking place at 3:15 p.m. Pacific, 6:15 p.m. Eastern, as the space station and Dragon were traveling 260 statute miles over Indonesia. Dragon has since completed 2 of 4 departure burns and exited the keep-out sphere. Again, that is that 200-meter invisible boundary around the International Space Station. We are now about 5 or so minutes away from Dragon crossing the approach ellipsoid to set the spacecraft and crew-10 up for their path back to Earth. Dragon is now about 500 meters away from the International Space Station. Again, that range and range rate continuing to increase as it continues on its departure. Again, Dragon is targeted to splash down off the coast of California tomorrow, August 9th at 8:33 a.m. Pacific, 11:33 a.m. Eastern, marking the completion of their 5-month science and research mission.
Of course, if you're following along, you've noticed that in the bottom left-hand corner of your screen, we have updated the telemetry that we're sharing with you, now tracking the speed and altitude of the Dragon spacecraft. There we've got a shot on board on your screen right now of on board the Dragon spacecraft. Our crew inside has been given the go to doff their suits. Generally speaking, we always have the astronauts in their suits when we're in dynamic phases of flight. That's because the spacesuits are effectively an extension of the spacecraft. If we needed to for any reason, the spacesuit is designed to keep the astronauts safe. Now that we've cleared that dynamic phase, it's time for them to take those suits off, get a little bit more comfortable for their 17.5-hour journey home.
And then they will put those suits back on just before they begin that deorbit phase. So they'll have a little bit of time to get some sleep, get a meal, and really settle in, since it is a 17.5-hour journey. Again, we are about 5 or 6 minutes away from exiting the approach ellipsoid. Again, that is that 2 kilometer by 4 kilometer invisible boundary that we are waiting for Dragon to exit. And once that happens, crew-10 will no longer be in integrated operations, and you did hear them setting up some of the communications directly between SpaceX Mission Control and Hawthorne and crew-10 aboard Dragon, so it'll be a direct communication with them without the station crew in the loop there. And right now, Dragon is about 600 meters away from the International Space Station, as the International Space Station travels about 260 statute miles over the Pacific Ocean off of the coast of Japan. And the International Space Station does go through an orbit every 90 minutes or so. And when we had that undocking, you could see the sunrise. So they were coming into an orbital daytime during that undocking, and that is actually why the undock was delayed by about 10 minutes, just to allow better comms and to get those great views from the International Space Station.
As you mentioned, because we're orbiting the Earth roughly every 90 minutes, our crew-10 astronauts and those astronauts still on board the International Space Station are seeing about 15 sunrises and sunsets every day.
And there on your screen, you're seeing a live look inside the SpaceX Mission Control here in Hawthorne. Again, the Dragon and the International Space Station do go in and out of signal as they transition satellites, which is known as a loss of signal. And then once they reacquire signal, that'd be acquisition of signal. And there you can see a live look of Dragon from the International Space Station. And those cameras on the International Space Station are actually controlled by a flight controller and mission control in Houston known as Cronus. So they actually manually work to follow Dragon during its approach, as well as during its arrival and docking, which happened back in March.
You You can already see, as we get this last glimpse of Dragon as it departs the station, how much smaller Dragon is from these cameras on board the International Space Station. We talked about this a little bit earlier, but even though the rate of separation between these two vehicles right now is smooth and steady, which is exactly how we want it to be, they are both traveling about 17,000 miles per hour, which is a just tremendous amount of speed and energy that we have moving between these vehicles. So it's important that every phase of this process is planned, carefully executed, so that we understand what's coming next.
And right now, Dragon is about 750 meters away from the International Space Station. So again, continuing to increase that gap between the space station and Dragon as we continue to await confirmation of approach ellipsoid exit. And there on your screen, you can actually see a map which depicts where Dragon and the International Space Station are flying. Again, they're flying over the Pacific Ocean.
We have kind of the zoomed in view here available on your screen right now, but you can always see our position relative to the Earth in the bottom right-hand corner of your screen. You can see that little light where we have Dragon over, again, the Pacific Ocean. And then right next to that, you can see a map of Dragon's Draco thrusters. Each of those little white puffs that you see are small adjustments that the Draco thrusters on board Dragon are making to control its position. In spacecraft, we generally refer to that as the spacecraft's attitude, but we are talking about the relative 3D orientation of the spacecraft.
And right now, that range rate is about 1.1 meters per second, so slowly starting to increase that speed as Dragon continues to make its departure from the International Space Station. As we stand by for confirmation of approach ellipsoid exit, the Dragon spacecraft is currently over 830 meters away from the space station. Again, this is following its undocking and physical separation about 18 minutes ago at 3:15 p.m. Pacific, 6:15 p.m. Eastern. And following the physical separation, which required those two short undock burns, we did have 2 departure burns, and that was the first 2 of 4 departure burns. The depart burn 2, which is the 3rd departure burn, will be coming up about 30 minutes or so after approach ellipsoid exit, and then that will be followed by the final departure burn, depart burn 3, before they get into those phasing burns and then set Dragon up for its deorbit burn early tomorrow morning ahead of splashdown off the coast of California.
We talked about this a little bit earlier on too, but following that phasing burn, Dragon is going to complete deorbit reentry and splashdown. During our deorbit sequence, several events are going to occur, including trunk separation, closure of the nose cone, a deorbit burn, deployment of our drogue and main parachutes, and finally splashdown.
And then after splashdown, there's still quite a few activities that have to take place to actually hoist Dragon up onto the recovery vessel. The recovery vessel for this is the Shannon. And so the recovery team is getting staged out there. The boat is on its way to the splashdown location, and then there will be a set of helicopters that take the recovery team out to the boat, and they also have 2 fast boats, and so those fast boats will be the first ones out to the splashdown location following that 8:33 a.m. Pacific splashdown tomorrow morning, and they do some initial checks to ensure the safety of the spacecraft before they begin safing it to prepare to lift it up onto the recovery vessel.
And of course, once Dragon is on board our recovery vessel, we're going to help the crew egress or exit Dragon. And then we'll also do some quick recovery of the time-sensitive scientific experiments and cargo on board, sending those to different research labs
Dragon
all around.
SpaceX on the big loop. Dragon has exited the approach ellipsoid and is on a 24-hour safe free drift trajectory. Configure comm for Dragon aground in preparation for disabling the big loop.
SpaceX Dragon copies. Thank you.
And And so we did hear confirmation just now that Dragon has exited the approach ellipsoid. Again, that is that invisible boundary measuring 4 kilometers by 2 kilometers by 2 kilometers, and the same family as the keep out sphere. And vehicles outside of it have to be on what we call a 24-hour state-free trajectory, which means the spacecraft would not cross into the approach ellipsoid for at least 24 hours, again, even if it lost all maneuvering. So now that Dragon and Crew-10 are well on their way back to Earth to conclude their 5-month science and research mission aboard the International Space Station, let's check in one more time with Rob Navius and Mission Control Houston.
Thanks, you guys. You mentioned some of the critical activities that are coming up. The most critical activity tomorrow for the Endurance crew will be that deorbit burn that you mentioned. That will be a 17.5-minute retrograde firing of the Draco thrusters, basically a braking maneuver to slow Endurance down by 115.4 meters per second, allowing it to drop out of orbit for its high-speed entry back into the Earth's atmosphere. The direction of travel will keep the heat shield in the direction of travel to repel the temperatures that will build up to some 2,500 degrees around the spacecraft and its 4 occupants. Here in Mission Control, the team led by Flight Director Alison Bollinger is now winding down its activities. The crew on board the station moving into a pre-sleep period. They will wake up in time, however, to watch all of the critical activities that will be uplinked to them for the return of Endurance and its parachute-assisted splashdown in the Pacific Ocean. So with that, we'll wrap it up here in Mission Control in Houston and turn it back to you guys in Hawthorne.
Thanks, Rob. As you mentioned, with that, Crew-10 has officially departed the International Space Station. It's going to take them about 17.5 hours until they make their way back to Earth. The crew is currently doffing or removing their spacesuits to settle in for that ride home. As we've mentioned previously, Dragon is targeted to splash down off the coast of California at 8:33 a.m. Pacific time tomorrow, Saturday, August 9th, followed by the crew getting picked up at sea by a SpaceX recovery vessel. As they rest up, our teams here will continue to keep an eye on the weather to ensure a safe return for Dragon and our Crew-10 astronauts.
And although our undocking coverage is concluding for today, you can continue to follow along with Crew-10's journey back to Earth by listening to real-time mission audio, the same operational communication used by flight controllers on the ground on NASA's YouTube channel. Meanwhile, we will rejoin for live visual coverage starting a little more than 1 hour prior to splashdown at 7:15 a.m. Pacific, 10:15 a.m. Eastern tomorrow. And as always, you can find mission updates on X, at NASA, at SpaceX, and online at nasa.gov. Thanks again for watching. We'll see you soon, and our Crew-10 astronauts back on Earth very soon.
that we didn't encounter any sort of pirates or causing any disruption to our shipment. In the maritime industry, you can track ships everywhere they go. As we were departing from Seal Beach, there were posts on the internet because there is a vibrant community of people that are very interested in what's happening with JWST. And so on Reddit, actually, there was one particular person that was really good at tracking the ship, and he was giving a great log to the general public of where the ship was going. I was actually able to reach out to him, explain to him, you know, it would be great of him to maybe just add a little bit of vagueness to where the ship was actually going, the direction, just a little bit less detail. And surprisingly, he was great about it. You know, he went about posting and saying that it got a little bit more generic with the locations.
Kourou is actually a good place for a launch site, very close to the equator, and that helps you getting an extra spin when you launch.
It was a bubble that we were there, mostly hidden from the pandemic, able to work and just focus on Webb and getting it ready for launch.
The weather's pretty volatile. I mean, you're in a tropical environment, even in December. In fact, caused one launch delay of a few days. Under the umbrella of that launch delay, no pun intended, the technical folks preparing Webb for rollout had a bit of extra time to be able to attend to last-minute preparations.
It was pouring. I got soaked more than I had any other time in Peru. Standing out there with the team, watching it rolling out to the launch, and it is an absolute party in the rain.
We weren't going anyplace until Webb was off the ground safely on its way. So it's not like we had a plane to catch or a train to catch, right? We were a captive audience.
A really neat thing happened because of the way that launch had been delayed, and it ended up being on Christmas Day.
So when the clock hit 12, you know, it was a privilege of mine to wish everybody a happy holiday and to thank them and then mention to them that their families were, you know, history had put them in that place at that time for a reason, you know. And I didn't go into it, but it was like, you know, I kept thinking about the Apollo 8 launch, you know, Christmas Eve, you know, reading about from the Book of Genesis. You know, it's famous, right?
It's now approaching lunar sunrise, and for all the people back on Earth, the crew of Apollo 8 has a message that we would like to send to you. In the beginning, God created the heaven and the earth, and the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters, and God said, "Let there be light," and there was light.
They're reading about, you know, the first light, and here we are launching this incredible machine that's intended to pick up that first light.
When the Webb telescope was launched, I was just sitting on the sofa with my wife because COVID was happening, so everybody stayed home. We didn't have any launch parties. Okay, well, that's how it goes. People thought, well, surely you must be on the edge of your chair because you've been working on this forever and it could go wrong. That's not how I felt. I felt, of course it's going to work. We've done everything we should do.
I haven't yet thought a lot about what is the proper Zen mode to get into for launch day. By that point, the die is already cast, right? Either we built it correctly and it's going to work, or we're going to find surprises on orbit, but it's time to go find out.
It's all looking very good here at the spaceport for a Christmas Day launch. Operations running smoothly, the countdown ticking over nicely. All the systems are green and we are go for launch. We're looking at launch pad number 3, the James Webb Space Telescope, inside the very top of the rocket in first class with its seatbelt on. I'm in the Mission Control Center here at the spaceport, the Nerd Center of Operations. We're about 10 kilometers from that pad, and behind me you can see it's a laser focus here in the control center with the mission control centers all on console there as we get closer to launch.
Can just go to black? Particularly when I would tell you.
Merry Christmas from the Guyana Space Center in
Peru, French Guyana.
You know, they do Ariane 5 launches frequently out of French Guiana, but there was something different about this one. There was something in the air that said, this has a different aura, this has a different importance, this one had a different flavor to it, and you knew you were in the middle of something big.
You get the 2-minute warning. Everyone goes out onto these balconies.
And you were watching a number of people, VIPs and invited guests, moving out to the observation platform that is right next to the Jupiter Control Center as we stand by for the 1-minute call from Jean-Luc Voyer.
À tous les vidéos, attention pour moins 1 minute. Top, à 0 moins 1 minute.
Thumbs up from Jean-Luc Voyer. All systems are go. We're inside a minute now. T-minus 50 seconds and counting.
And you wait. And you can hear a little speaker with Rob's commentary.
Turbo pumps will come up to flight speed for 7 seconds, and the command will be issued to ignite the solid rocket boosters. The James Webb Space Telescope will be on its way.
And then he starts counting down.
T-minus 30 seconds and counting.
By the time he got to 8, my throat was just closing.
Standing by for terminal count.
À tous les vidéos, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Because we were a few miles out, you see it go, and it's going up and up and up and up. You don't hear it for at least 45 seconds to a minute. You know, all of my hopes and dreams and wishes and frankly, a piece of me launched at that time. And you see it go, and it's such a strange thing to only hear it, and it just rumbles.
And liftoff.
Décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
It's a really specific, odd rumble that a rocket has leaving the atmosphere that also keeps it special in your memory because it's something that is very different than sounds that you hear any time else.
Just over a minute from now, Springs will gently push Webb away from the upper stage of the Ariane 5.
There's this loop running in your brain where you're like, did that just really happen? You know, did we just really take off after multiple decades at this? Did we just really leave the Earth?
Séparation Webb Space Telescope. Go Webb!
Ironically enough, as we marvel on this view from the upper stage camera, this will be humanity's last view of the James Webb Space Telescope as it moves to its workplace about 1 million miles away from Earth.
The launch team is done. Now all the attention turns to the operations centers.
For those of you who are just joining us, we are looking at live coverage of the deployment of the secondary mirror for the James Webb Space Telescope. You're looking at an animation that includes real-time telemetry, real-time data from the spacecraft as to the configuration that it's in.
We used to make jokes. It was like, hey, Merry Christmas. Look what we got. We got a telescope. Oh, some assembly required. Yeah, it was some assembly.
We started getting our deployments started, and Webb was performing beautifully.
You're seeing an animation, but this isn't just any random animation. This is actually based on real data.
That script looks good. You're go to execute.
Roger, executing.
Command will fire OTE LRM Group 5. OC, you're go to fire.
Copy, go to fire.
It's not just pushing buttons. There's a lot of real-time information that comes in, and you've got to be able to deal with it. You've got to assimilate it, figure out what to do, and make an action.
I'm getting more and more excited. My heart is starting to beat faster and faster. For me, there's a tremendous amount of joy. I mean, I have this smile like on my face from ear to ear right now.
Again, we had rehearsed everything and practiced it a zillion times, but now you're up there and you only got one chance to get it right.
Without this mirror in its right position, we do not get light into the telescope.
Motor move has completed successfully, and Deplead has confirmed we are go to proceed with the latch to safe.
Roger, executing.
We are now at a point where we're about 600,000 miles from Earth, and we actually have a telescope. So congratulations to everybody.
Well, I'm thrilled to see that it finally works, because when we started off, we got a lot of people laughing at us that was impossibly difficult. And now it's done.
Hey, John, how are you doing?
Hey, John. Well, when we built the equipment, we drew our requirements up, they're all numbers. Nobody tells you what that means in terms of the beauty of the universe. Years and years ago, people asked me, John, are the pictures going to be beautiful? And I said yes, but I didn't know what they'd be like. So it was an act of faith, but it was a good act of faith.
Whatever's out there, we're going to see it. We haven't cranked this sucker up to 11, but we're going to.
When things got cold enough, the cameras worked. Saw those first images, and it's like, yeah, this is pretty cool.
We're really, standing on the backs of thousands of people over many, many different disciplines to make this happen.
The image came back. There was the beautiful center image of the star with 6 radiating rays of light. And there's supposed to be nothing behind it. Nothing. What we saw turned out to be 250 galaxies that have never been seen before in this image that supposedly had nothing in it.
There are galaxies everywhere. People said we've been photobombed by galaxies. So, well, that's a pretty big thrill for everybody.
I didn't know I was coming to a pep rally today. But that's all the better. And you've got a lot to be rallying for. This morning, folks across this planet are going to see the images captured by this telescope. This telescope, because of infrared, is going to be able to penetrate through the dust clouds. You're going to see the formation of stars. You're going to see devouring black holes.
Here we go. Let's do it. Okay, we've got the whole world watching. Are you ready to put the first image up? Oh, let's do it.
We are ready to see Webb's first image of a star dying, a planetary nebula called the Southern Ring.
Art that is out there in the sky, revealed for the first time. We're thinking of the team and we're thanking them. John, thanks to you. Thanks to all of you.
I think people brought some champagne. So that's higher priority.
You're going to see things that this species has never seen. And you've done it. Tell everybody this was an important day in the history of humanity. Because we'll never look back. You can never undiscover, you can never unobserve things. So congratulations to the entire team. You've all made history. Be proud. Thank you for your
And, you know, I'm a scientist, so I've been working on this project for 20 years, so we should expect what we saw. But no. Several times in the last 6 months, I nearly break my jaw of what I saw. These incredible images.
Success is binary. You either win or you don't. So we built something that was so ambitious. If it didn't work at all, we would be terrified. But if it did work, we would be guaranteed of tremendous discoveries. I think my favorite image is the picture of a cloud of galaxies with a very, very bright one in the center.
100 years ago, we thought there was only one galaxy. Now, the number is unlimited. And that light that you are seeing on one of those little specks has been traveling for over 13 billion years.
Everywhere we look at is going to be a scientific discovery. I believe that.
Oh, no, I agree.
And every image is essentially a whole deep field.
Yeah.
Is that incredible or what?
This stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. Today, for the first time, we're seeing brand new stars that were previously completely hidden from our view.
I present to you Maisie's Galaxy, which is named after my daughter, as we both discovered it on her 9th birthday, and she had been asking me for months to name a galaxy after her. I would like to leave you with one of my favorite images.
It's called Stefan's Quintet, and it's wondrous.
From the perspective of what we're going to find out, what do you tell a 7-year-old when she says, I get what the Curiosity thing's doing, but what's JWST going to do, Dad?
Okay. She's got a good question. What we're actually trying to find out is the entire history of the universe from then till now, from the beginning till now, including the things that made galaxies and stars and planets and Earth, and made it possible for us to live on our particular little Earth. So that's why I'm interested. I asked my dad that question sort of like that, and I said, well, where did we come from? I was about 6 or 7 or something. Nobody knew. We knew a little bit, but we certainly couldn't tell you the whole story.
You know, we can get as geeky and as in the details as you want, but when you step back for a minute, it really is about our place in the universe. And that's something that resonates with people, and that they hit people in an artistic and a spiritual way.
I'm reaching out to you from London.
My father was diagnosed last year with stage 4 cancer.
And unfortunately, the prognosis means he doesn't have a great deal of time left with us.
From as early as I can remember, my father has been out burning the midnight oil looking at the stars through his telescope.
And often driving into the mountain overnight, setting up to take pictures and even submitting photos of what he found in magazines.
When I was a kid, I remember him upgrading his telescope every few years after saving away.
He is so passionate about the work you do, and the recent advancements of the JWST has been very exciting for him.
I'm really pleased he's still here to follow along with all the amazing innovation you and your team are doing at the moment.
He keeps busy keeping up with the news around your advancements. And that's really cool.
For me, these letters express how I feel. These letters are about the wonder that I feel looking at the universe the wonder that I feel looking at our team that made this observations and tool possible, astonishment at what we're able to discover.
It's kind of beyond words to describe how satisfying and fulfilling and rewarding it is after reading things like this. I mean, yeah, it's pretty hard to describe. It really makes you feel good about what you do, and to make a mark for good and for positive things in the world is pretty cool, pretty special.
That's actually why I do love space, and I think that other people love space, because it does give you that sense of awe and like feeling one with the universe. So I'm glad it helped someone.
Look, there aren't many things these days that almost everyone on planet Earth can feel inspired about. But I feel like the images from Webb are one of those things. They bring in a sense of wonder. It's kind of like when you're a little kid and you look up at the night sky. We need some wonder in our world. It's just a feeling of immense joy and achievement. And I feel happy for humanity a little bit, yeah.
So I'm lucky enough that I get to continue telling the story about what NASA's doing for its next big flagship missions.
There are plenty of other mysteries of science, but we are seeing with our own eyes, with the aid of telescopes, the process unfolding. So what more could you hope for from astronomy?
One of the core obligations we have is oversight, and we quite often hear in government how things don't work. I just want to say thank you for exceeding our expectations, and let's continue, and with that I yield back.
So congratulations to everyone for making it happen, and we now are counting on continued brilliance for the next half a century at least. Thank you for proving it's possible. Looking back to childhood, we had no idea. No one had any idea what the future would bring in terms of space exploration, new technology, electronics. It was all new, and we had no idea that computers would ever be so powerful or so common. Marvels are yet to occur, and we are still growing rapidly in our capabilities. So astronomers have already a book that we've outlined what we'd like to do for the next many decades. I think it'll take us a century before we run out of that book. And then from what we learn in the next decades, we'll have more miracles to produce, more miracles to ask for. So much is possible, and this is a very exciting time to be an astronomer.
I get to see things that are way beyond Earth because of where I work.
That will surely surprise us in some way that I can't tell you.
It's an exciting moment. This thing's been a long time in the making.
And once we get it out there, we got to robotically put it back together. That's never been done before.
Pride in humanity, that when we want to, we can do that.
We're building this telescope really to answer fundamental questions that we have.
It's detecting the building blocks of life on exoplanets.
That then gets sent into the telescope.
All these galaxies in the background photobomb the pictures, right?
I feel like we're discovering new parts of the universe.
It's going to raw inspire us as people, or it's going to solve a problem we didn't know how to solve because we're going to learn something that we didn't know until this big eyeball in the sky opened up and saw it. I don't know who else gets to say that.
The James Webb Space Telescope is the most ambitious and complex space science mission humanity has ever undertaken.
No one's ever done anything like this before. The science will be worth the wait.
Roger all, Discovery.
astonished to see the dust cloud annihilated when the massive stars exploded.
Now Webb takes us even deeper into the infrared universe.
Attention on 232, this is the launch director performing the final poll for launch. Verified no constraints and go for launch.
Program chief engineers have no constraints and are go for launch.
I have no constraints and are go for launch.
Weather has no constraints and weather is go for launch.
You are looking at the world's most powerful rocket. Artemis 1 embodies the hard work of thousands across the world, determined to explore for the benefit of all.
After years of testing and talking and testing some more, Artemis 1 finally carried the dreams and aspirations of the world back to the moon.
I knew this would be an exciting mission. I mean, we haven't left low Earth orbit in over 50 years. Nobody on my team had done it. Most of them weren't even alive back when we did it last.
It has been a culmination of many years of hard work. It certainly represents a lot of that design and effort that we have put in to build the first human spacecraft for NASA in over 50 years.
It sent a message to the world that we have laid the foundation for a generational rocket.
We are not just going to the moon, we're going to prove that we can live and work on the moon and establish an outpost on the moon for future distant exploration out to Mars and beyond.
I'll never forget coming in the afternoon and everything is just working per the timeline and you're starting to feel like, you know, today might be our day.
Great news, no constraints to launch.
You know, I'm sitting on the console at my station and things have been pretty quiet and, you know, you start to get this sense like this thing's going to go this time.
And here we go.
In the wee hours of that morning of November 16th came, it all fell together, and the payoff was a launch that shook you to your foundation and signified that America was back on the road to the moon.
And when that vehicle lifted off the pad, the windows began to shake. And the building announces that that vehicle is flying.
I was overwhelmed with joy and excitement, not just so much for me, but for the entire team, for the country. It was eye-watering.
And I was tearing up. What an amazing accomplishment for this team.
I'm still shaking a little bit. That never gets old. That is always one of the coolest things you'll ever see in your entire life.
Just like, oh my gosh, the adrenaline rush just hit you. And I knew this is it. It's game time. We're off and running now.
For the first time in 50 years, we were breaking out of low Earth orbit to head toward the moon.
And attitude for solar array deploy. Saw deploy initiated. Copy. 5 4 solar arrays released.
After the vehicle was put in its preliminary orbit, meaning Orion and the ICPS, we had to wait for translunar injection, and that was a whole different game.
Let's go have a big burn and let's go to the moon.
Let's do it.
Now, if you think about hitting a keyhole in the sky, it was all about that translunar injection burn from the ICPS. Without a perfect burn from the ICPS, we weren't going to the moon. We certainly weren't going in the right place.
That little RL-10, the engine that could, went on, and that it's the longest burn it had ever had in the history of the RL-10 program, which goes back many, many years.
SLS set us up for success. The launch vehicle and the insertion point was over 99% accurate to where they predicted.
Orion is now flying free, attached to the European Service Module and on its journey to the moon.
We had video from Orion shortly after the translunar injection burn was complete.
Orion flipped around and we took pictures of the Earth, and I had no words. It was just amazing. Amazing.
The views of our blue marble in the blackness of space, now capturing the imagination of a new generation, the Artemis generation.
It was 4 days to cross the line of demarcation to enter what is called the lunar sphere of influence, and you could see the Earth beginning to recede.
Our first big burn was the outbound powered flyby, which is the one where we went right by the moon. Orion was actually on the backside of the moon, so we did not have communications with it, so we had to set everything up ahead of time. And we lost the signal. We waited, held our breath, said some prayers, and then sure enough, it came out from the backside of the moon, and we were on our way to the distant retrograde orbit.
Distant retrograde orbit, we're going to be about 38,000 miles away from the lunar surface.
Artemis 1 traveled approximately 268,000 statute miles from Earth.
One of the really fantastic moments during the mission was where we saw the first image of the farthest point that any human spacecraft has gone before. We see these images downloaded real time, and we would sit in the rooms and we would just pause the meeting. We'd pause the discussion, go, look at that picture. It's almost unreal. They really represented as if we were there on board the spacecraft, looking at the moon and looking at Earth, our home.
We're continuing to get some spectacular views from the Orion spacecraft. Orion now has its sights set on home.
NASA's newest moon explorer, now less than 2 hours away to complete its shakedown mission.
When you hit the Earth's atmosphere, entry interface, we did what we call a skip entry, where Orion bored down into the atmosphere for a period of time, then it popped out, and then it skipped upwards of, it was thousands of miles.
And if you don't come back into the atmosphere with accuracy, you will skip out of the Earth's orbit and not be able to return.
And we did that intentionally because we wanted then to come back down and do a second heating cycle. We're coming back into the atmosphere, basically a double heating, to really stress the heat shield.
It's hard not to hold your breath when all of that's happening, because I'm thinking to myself, if this doesn't go well, what do I do? What do I have?
That was the major objective of Artemis 1. We had to prove that that heat shield would be rock solid to sustain a crew, because if you don't ablate the heat, you're done.
And there it is, high over the Pacific, America's new ticket to ride to the moon and beyond now in view.
Finally, on re-entry, that was a culmination of that 25-day mission that we waited with bated breath to make sure our baby came home.
Splashdown, Orion, back on Earth.
And when it hits the water, everyone just goes. It's just a rush to get to the capsule as quickly as we can. And so the teams, they feel the sense of urgency. The small boats move, the helicopters move, we're taking imagery from the air. We handled the recovery capsule like it was a fragile egg. We wanted to make sure that the heat shield got all the data that they needed, that everything, all the mechanisms were preserved.
From Tranquility Base to Taurus Littrow to the tranquil waters of the Pacific, the latest chapter of NASA's journey to the moon comes to a close.
You could sense a sigh of relief in the flight control room in Houston, knowing that our job was complete. We had brought Orion home successfully and set the stage for grander things to come in the future.
It was a testament to the hardware, but it was a testament to the teams, all of the teams that had a hand in bringing that hardware together.
We